Hello, in this part of the course, we're going to be moving into a new section, which is machine learning. There's a lot of material we're going to cover, but at the same time, it's really the tip of the iceberg for all the material you can do in this field. Let me try to start by relating to something that we're familiar with, and then connect it to something new we're going to be doing, which is building models. So all of you have been running functions for a long time, right? So, hey, maybe I'll write this code, and then our function take inputs, maybe in the form of parameters, and then they have some outputs. Maybe I'm either printing something or I might return a value. And so, for example, I can imagine that a function could be doing something like making some sort of prediction. Maybe my input is that I have some details about a house that's for sale, and then I might be predicting what it might sell for. And so when I have a function like this, that's an example of a model. And I could imagine having it feed in a bunch of values at the same time and making a bunch of predictions. So the idea of machine learning is that instead of having a computer write these, or instead of having a human write these functions, we're going to have a computer automatically generate these functions. And the way they're going to do that is they're going to learn by example. So we'll feed in a bunch of training data where we have a bunch of different houses that have sold for different amounts and have different bedrooms and baths. We're going to try to infer things like, well, how much is a bedroom worth? How much is a bath worth? How useful is it to have a newer house? And then based on that function, we're going to be able to generate that function and then use that to make predictions on other data. And you can imagine why that might be useful for a lot of things. Maybe you're doing property assessments, or maybe you're a realtor and you're trying to figure out how to price a house properly. So the example I've given here is an example of a regression model. And a regression model is kind of more broadly a type of supervised machine learning, which is one of the main three categories of machine learning. So I'm going to start broad now and talk about these three areas, and then we're going to be talking about regression in more detail, and I'll actually explain what it is. So the three main areas of machine learning are reinforcement learning, which is basically a situation where you have to make a series of decisions, and you're trying to optimize some sort of reward. So you could imagine some sort of robot moving around in the world and picking up coins or something like that. We're not going to be doing that kind of work in this class. Instead, we're going to focus on two areas, which are supervised machine learning and unsupervised machine learning. And in both of these cases, we just have all our data up front, and we're trying to gain information about that. Some people will say there's a fourth category of machine learning called semi-supervised, but we won't be talking about that here. Within supervised machine learning, there are two different things that we're going to learn this semester. One is regression, and with regression, we're trying to predict a quantity. And then with a classification, we're going to try to predict a category. So in any of these cases where we're trying to predict something, that's known as a supervised problem. And the way it works is, well, the data we have has some labels on it. Usually there's some special column that's telling us, a quantity, like the price for a house or some sort of category. And then from that, we can try to predict that label in cases where the label is unknown. In unsupervised learning, there's no special label column that we're trying to predict. We're just trying to look for general patterns in the data. And so we might do a couple things. One, we might try to cluster our data where we're placing rows into different groups. Or we might try to decompose our rows. We might notice that, I might have these rows which each have 5 numbers in them. But maybe every row is like a combination of kind of 2 component rows. And so there's some simplicity in there, even though there might be a lot of columns in our data. So I'm going to go through these 4 types of thing that we're going to learn this semester and just try to make it more concrete. So here I have a table, right? This is just a regular data frame. And so this is my index here. Here are my column names. Right now I have a Y column, which is my label. So that's going to be generally what I'm trying to predict. And then I have these different columns here that I guess I'm just calling them x0 through x4, but usually those would have some sort of real name, right? Like before I saw that we have like the number of beds in a house. So this label that we're trying to predict is, what we're going to try to do is look for a relationship between that and these other columns, which we're going to call features. And so in general, what will happen is that we have some examples, some rows where we have examples of both. And then there might be some other data where we only have the features, but we don't have the Y label. And so we want to try to predict what should go in here. And you can imagine why that might be. Maybe these are all different houses, and some of them have already sold, so we know what they sold for. And then these have not gone on the market yet, so we're trying to predict, well, what would they sell for if they do go on the market. Right, so the problem here with regression, I just want to state again, is that we want to predict a quantity, the Y column in this case, based on the features, right? And by a quantity, I mean this is like a number. So how are we going to do that? Well, we might actually break it down into 3 parts. First, we might select a subset of the data that we for which we know the answer, and then we might leave some other data aside for which we also know the answer. And what we'll do is we'll run an algorithm that is able to infer what the relationship is between these features and these labels. Once I've done that, I might run my model on these other ones for which I also know the answer. Now, of course, I already know the real answer, and unless my model is perfect, it's probably going to give me somewhat different answers. And so why would I do this? Why would I want to make a prediction if I already know the answer? And the reason is that I can do this to evaluate my model, or I might say test my model. So for example, if my model says that this row should have been 70 and it's actually 72, well, that's an error. Same thing here, 60 versus 59, that's an error. And I can try to quantify all of these errors and then give my model some sort of score, right? That's the testing phase. So after that, after I've learned my model up here and then I've kind of evaluated it on some known cases, then I might actually put it in production. Production means I'm using it for real things, and I'm trying to predict actual unknowns in the world. Like, for example, if I add a new house to the market, what might it sell for? And I could come up with these different values there. Another thing we might do, even beyond making predictions, is that I might look at that model and just try to learn things about the world. So I keep going back to the example where we're selling houses. I think it's interesting to just know, well, for each additional house, or for each additional bedroom or bathroom I have in my house, how much does that increase the value of my house? And I could use that to make different decisions, right? Like maybe I want to do a housing remodel. Am I going to get more benefit by adding another bathroom or another bedroom? Right, so we can just kind of learn things about the world and also make decisions in that way. Okay, so all of this was regression, which was the first kind of supervised learning we're going to learn this semester. And when we're doing these regressions, right, the key thing that makes the regression is that we're trying to predict some quantity in our Y label. Now, it's totally possible that our features might be a mix of both quantities and categories, right? So something like green, red, blue is a category. Something like shape is a category. A lot of things that are strings are categories. That's fine, right? The distinguishing characteristic of a regression is that the label column is quantitative. If I somehow am working on a problem where my Y is categorical, then this is no longer regression, it's a classification problem. But otherwise, all these other things I've been talking about where I kind of do training and testing and then I put in production, all of that is the same. We're just dealing with categories instead of quantities. Okay, so moving on, we saw the 2 kinds of supervised learning, which is both regression and classification. What about unsupervised learning? The main thing here, the main point is that there is no label column, right? I just have a bunch of features. And then I can try to still learn some patterns about this, even though I'm not trying to predict anything. And so one of the things I might want to learn is, well, are there any sort of natural groupings of these rows? And so there are algorithms out there that will, let's say, put all of these rows into 3 groups, and it might assign them numbers like 0, 1, and 2, right? And then just to kind of draw what that looks like, well, all of these rows belong together. Now, I really want to stress here that there's no data out there that tells me what the proper grouping is or even how many groups there are. So when I'm doing this, it's not exactly like there's one right answer. But that doesn't mean that all groupings or classifications are equal. I can measure within a group how similar those rows are to each other if I have some metric for that. And so then my goal is to have a grouping that kind of maximizes the similarity within each group. And there might be different groupings that are equally good, right? But as long as I'm kind of having a high similarity within groups, well, then I still learn something meaningful. And you can imagine lots of different reasons I might do this. Like maybe each of these things represent a different user for my web application. And if I can say, hey, well, there's these 10 different kinds of web users for my application, I could maybe run a different marketing campaign for each of these different groups. Okay, so clustering again is unsupervised, and it's unsupervised because, well, there was no label column I'm trying to predict. The last kind of machine learning problem we're going to talk about this semester, and which is probably the most complicated, is called a decomposition. And decomposition is also unsupervised, is again, right, there's no column I'm trying to predict here. And the idea with a decomposition is that I'm going to look through all these rows, and see if there's any pattern. Are there kind of a couple archetype rows that really can be mixed together to create other things? So maybe what I see is that with some small error, most of these rows are just combinations of these three rows over here, and I would call these my component rows. So you notice the columns are the same, right, between my original data and my component rows. And then to get this row here, like -11, -7, 3, 20, 20, what I would do is I would multiply this row by -11, and then add it to 21 times this row, and then add it to -8 times this row. All right, so I'm kind of taking a weighted average of these three rows to produce this row. And if you actually crunch these numbers, you see that I would get something kind of similar to this, but there would be some error, right? It's not a perfect match, which is fine. I mean, the fewer components I have, well, then I can have a simpler model, but well, there might be more error. So I have that here, right? I have these numbers here, and what we'll generally do when I'm trying to mix these components to create a row is I'll put these numbers in another table down here. So this will be a table of all my weights, or maybe my principal component scores, and so I'll put, you know, -11 here, 21 here, and then -8 here, and then for this next row down here, right, I'll do the same thing. I'll say -43 here, 12 here, and then the -6 here. And so since I'm doing this, I'm putting kind of these mixtures for every row down here. What that means is that if there's n rows over here, then there are also going to be n rows over here. If there are m columns over here, well, then there would be m columns over here. So basically what I can do is I can take this big table and I can reduce it to having some components here, and I can have some weights here. It's useful for lots of things. One is just if I'm trying to save space on my storage system, right? I can have these things be smaller. But then it's also nice if I'm trying to do other phases of machine learning, like a classification or regression. It's kind of nice if I only have like 3 feature columns instead of the original 5. That's trying to help me in a number of cases. Okay, so that's a whirlwind tour of these 4 problems we're going to solve: regression, classification. Those are both supervised because, again, it's labeled. Clustering, decomposition. There is no column we're trying to predict, so that's unlabeled. It's unsupervised learning. And so for each of these 4 things, there's actually a ton of different algorithms out there. And in this semester, we only really have time to learn like one algorithm for each of them. And so if I go to this website down here, this is the website for sklearn, which is the module we're going to be learning. And there's probably close to hundreds of different algorithms or different classes they have there. I put a small subset under here. And so I can see, well, here's all these different things they have for clustering. And we're going to just learn one of those, which is k-means clustering. Decomposition, all these different things I can do, we're going to learn just one of them, which is PCA. It turns out that for a lot of algorithms, the classification and regression come in pairs. So for example, here I have like a decision tree classifier, here I have a decision tree regressor, here I have a k-neighbors classifier, here I have a k-neighbors regressor. And that's why I didn't kind of split these out. I just put both of these under these 2 categories. And so we're going to learn 2 things here. We're going to learn logistic regression, and we're going to learn linear regression. And this is a little bit confusing because, well, this part's obvious, right? The linear regression is trying to be a regression here. This is the one that people get confused on, because even though it says regression in the name, it is not a regression. It's actually a classification, right? So these are the 4 things we're going to be learning this semester, and logistic regression is one people always get confused on because, well, it's not actually a regression. And I think once we learn all these things, the very nice thing is that the interface to using the other ones is relatively simple. So for example, once you know how to use a linear regression, you could very easily just replace the word linear regression with reg, and you're still going to be able to do all your machine learning stuff correctly. Now, before you do that, you should probably learn about how reg works and then think about which model is best for you. But at least in terms of the code, it's very simple to switch between different models within any of these 4 categories. So I want to talk a little bit, that was pretty high level, I want to talk a little bit about the foundations we're going to need to be learning this machine learning, both in terms of the code and then also the math. We're going to learn a few different modules. The main one is at sklearn. I was just showing some documentation from sklearn. We're also going to learn NumPy, which has lets us deal with matrices. It turns out that NumPy is really the foundation for pandas, right? All pandas data is actually stored in NumPy, and now will be a good time for us to actually see that. And then we're going to learn this thing called PyTorch, and PyTorch can do a couple of things for us. One is it can do calculus for us, which is pretty cool. Another thing it can let us do is it can actually let us run our code on GPUs, which are graphics processing units. Everything we've been running so far this semester has been running on CPUs, right? Your central processing unit. And it turns out that GPUs that are originally built for graphics are also happen to be really good at machine learning. And so a lot of things, if you're dealing with a lot of data or kind of complex models, a GPU will be better at it. We're going to have to learn a little bit of math. I'm not assuming you have any math background besides what you might learn in high school. But let me give you an example of how math is going to come into play here for a regression problem. Right, so we have this example again with all the houses and these characteristics, and then we have a function that predicts the price. How would we do that with matrices? Well, I might take all these numbers in a data frame and put them in this matrix here. And then for my function, I may have kind of just an algebraic expression, which is using matrices. So my x here is this matrix, c is a vector, b is just a number. And when I run this, well, I'm going to get this other vector out here, which actually has all the prices, right? So to understand what's going on here, we have to learn a little bit of linear algebra, right? This is not a regular multiplication. It's actually something called the dot product, and it looks like this, right? I can take this x matrix here, dot product it with this vector, and then add a number, and then that's how I'm going to get my results over here on the right-hand side to do one prediction, right? And what's cool, right, is that if I can do one row times this vector here, and I get one house value, and it's going to go through kind of without having a loop even, right? The beauty of linear algebra and multiplying matrices together with the dot product is that I can do it in one step, and I'm going to get actually all of these numbers. The code for it is pretty simple. If I say data frame.values, then x is actually going to be a NumPy array. And if I want to, I can just say, well, I want the dot product of these two things, and I want to add b, and it just works. So we're going to be talking about that in quite a bit more detail at some point before the end of the semester. One thing I want to note is that if you're reading other documentation, a lot of resources will use a instead of x, which I find confusing. I think that's not intuitive if you're kind of working in all of these scikit-learn modules, because those will generally use x for data. And then even stranger, right? We'll often have a c when we're in scikit-learn, but then they call that little x instead. So just be, as we're learning linear algebra stuff, I just want to say up front, and I'll say it again, be aware that the variable names are a little bit wacky. So what is kind of the scope of linear algebra, and what kind of things are we trying to solve? Well, one thing that we're not trying to solve is something like this, y equals x squared. That is not linear, right? Anything quadratic or cubic or anything like that, not linear. Really, all we can do is multiply variables by numbers and then add things up, right? So this is an example of a linear equation, right? I just have I have some different variables, right? And then I'm multiplying them by different numbers. One of the things we're going to notice is that the way we're going to be doing linear algebra in this course is we actually have very big matrices and a lot of variables and a lot of equations, right? So you can see here I actually have 50 variables. So I think the key takeaway is that more variables, more data, but simpler equations. What about calculus? So here I have that situation again with the house where I have some training data. So I have both my features and my label. It goes into an algorithm, and that algorithm will basically spit out this this formula for me that I can use to predict housing prices, right? Now, it turns out that when I was doing this training, right, I had the original prices, and the new prices might be a little bit different, right? This is 140, this is 190, 240, 254, right? They're all a little bit different. And so what I can do is, for this given equation I end up with, I can have some sort of function called a loss function that compares the correct answer with my model's answers, right? So I compare these two, and I get one number out, right? That's kind of like what my error is, or how bad it is. And of course, how bad it is really depends on kind of the numbers that are part of this equation down here. So the whole idea of this training thing with this algorithm is that I want to find out, well, what C can I do that is going to make my error, my loss, as small as possible, right? So we're trying to minimize something. And I don't expect you've taken calculus, but I know a lot of you have. And in calculus, we're often trying to minimize or maximize things. And that's why it's trying to come into play a little bit here. The good news is that we don't have to understand calculus. There's going to be modules that can do it for us, such as this PyTorch thing that we're going to be learning. PyTorch is also going to help us be able to run our code on GPUs. We're going to be able to do things like take two matrices, shove them over to a GPU, and then multiply them together, and it'll just kind of, it'll almost feel like it's just magically going faster than it would if we're running on a CPU. And it doesn't take a lot of code to move it around. So PyTorch is going to be very powerful, both in terms of calculus and using GPUs. To conclude this video, I just want to talk about this difference between developers and users, and then who we are. When I'm looking at this picture here, right, I'm feeding all this training data into a machine learning algorithm, and then that's giving us a function we can use to make predictions. There are classes and I guess people in general who either develop new algorithms or write code and optimize code for existing algorithms. And we'll just do a tiny bit of that, but that's not our focus. We aren't trying to do machine learning research or come up with novel ideas. We aren't developers. Instead, we're going to be users of machine learning algorithms that come in scikit-learn. And so some of the questions that we're going to be interested in going forward for the rest of this class is, well, which algorithm should we use in sklearn? How should we pick it? And I guess how should we configure it, right? A lot of these have different parameters. In terms of the data, how can we clean it up so it's trying to work well with the machine learning algorithm we chose? And then finally, when we actually use this thing, we're going to get all these predictions that we can compare it back to the original. And how do we want to score that? There's not necessarily one right way to evaluate how good or bad it is. And so we want to get some experience with that as well. So that's a bit of a preview about what's coming up in the course. And hopefully this is kind of a fun change of pace compared to what we've been doing. Hello, in this video, I'm going to be training a regression model from scikit-learn to some COVID data in Wisconsin. So here I am on the Department of Health Services website, data portal, and I can search for COVID here. And the data set I'm using is this one right here, the historical data by county. So there are about 70 counties in Wisconsin. And what this data shows me is for each day. I wonder if I can go to data browser here. It shows me for each date in each county all of these different stats. So for example, how many positive cases are there total? How many new cases are there? How about over the average of the last 7 days? And how many deaths are there? And ultimately what we're going to try to predict in this, based on this data, is, well, how many deaths are there 2 weeks in the future based on looking at the stats for today. So I had downloaded this, and I'm not going to do it again. And then there was a fair bit of data cleanup that I had to do here. And that's not the main point of this lecture, so I have a notebook for it that does all the cleanup. And I'm just going to kind of quickly walk you through this, some of the things I did here without spending too much time on it. One, I pulled out just a few interesting columns. So for example, how many positive cases were there on average over the last 7 days? And then how many new deaths were there? We had a bunch of missing data, so I just dropped anything with missing data. And then I converted the date to an actual pandas date time. And in the process, I dropped what hour it was. I just want to get the date without having the hour that it was posted. And then finally, the documentation for this data set says that negative 999 really means that there's less than 5 in whatever that field is. So it could be anywhere from 0 to 4. And so I think just for simplicity, I just replace that all with 0. We don't really know what that is. You could imagine doing something smarter like maybe 2.5 seems more fair in some sense. Anyway, so I get a data set that looks like this, right? And in a lot of cases, while there's no new cases and no new deaths, maybe for some of these smaller counties, and then of course for larger counties, this definitely is not 0. And so then I go down a little bit more. The other thing I want to do is I want to add a column which isn't just, well, how many new deaths are there, but how many new deaths are there 2 weeks in the future. And so I had to do some trickery with time deltas to basically join the data in 2 weeks in the future, and you can look at that if you're interested. But in the end, I get a data set that looks like this, right? I know how many new deaths there are on this particular day, and then this last field is how many there are after the specific one. And I saved all this to this Wisconsin COVID data set, so that's what I'm going to be working with here. And I'm just going to head over here and create a new notebook to analyze that. So let me head here, and then what I'm going to do is I'm going to import pandas for starters. So I'm going to say import pandas as PD, and maybe while I'm also at it, I'm going to import matplotlib.pyplot as PLT, and then maybe I'm just going to configure my matplotlib stuff first. Plotlib inline, and then plt.rc params. Let's just make the font size a little bit bigger. Great. And so now I can actually get my data frame. So I'm going to say data frame equals pd.read CSV. And what do I want? Well, that file I produced from that other notebook, which is Wisconsin COVID.csv. And let me just peek at that. So that's all good. And maybe just to make sure that all these things are not actually zero, I'm just going to say, what does the data frame mean? And so I can see on average in a given county and in a given day, on average 1 in 4 people have died. And so what I'm going to be trying to do is I'm going to try to be predicting this field on, I might either try this as a feature or this as a feature, and this is going to be my label column that I'm actually trying to predict. It's a quantity, which is why I'm doing a regression instead of a classification. Often before I jump into trying to do a regression, I'll do a scatter plot to just see if I can identify visually any patterns in the data. And so I might do something like this. I might say dataFrame.plot.scatter, and then I can say my x equals something, and then my y equals something. And so in both cases, the thing I'm trying to predict, my y, is how many deaths are there going to be 2 weeks after this given date. And then my x, I guess for the first case, I'll try the 7-day average, like that. And so I can see a picture there. And then the other thing I want to do is I want to say, well, if I look at how many deaths there were today, what will that tell me about how many deaths there will be 2 weeks from now? And I see a slightly different pattern there. Sometimes for these, I like to say alpha equals 0.2 or something like that, just to give it a little bit of transparency when a lot of points are on top of each other. And so I'll do that as well. And so the other thing that I'm really like to do as we're going forward is we're going to train a regression model on both of these variables. And so I want you to get a sense when we score that, how that score corresponds to kind of the strength of the relationship in both of these. So I'll start with this one. How can we train a regression model that fits this to this? And the first thing I have to do is I'm going to have to import it. So I'm going to say from sklearn.linear model import linear regression. This is the main regression model we're going to learn this semester. So I'm going to do that. And then if I want to, I can create a new linear regression object, just like that. And so there's a few methods that we're going to want to learn with this. So some important methods are going to be fit, predict, well fit, score, and predict. And we're going to be running those things on our data, right? So let me come down here and what I can do when I'm fitting it or training it is I give it 2 pieces of information. I give it my my x values, and I'll give it my y values. And for the y values, that could be a series if I want. So I could just pull out that one column. For my x values, it has to be a data frame. And so let me just take a look at my data frame earlier. What I'm going to do first is do a model corresponding to this plot, right? So I want to do it based on how do the deaths today predict the deaths in the future. And so what I have to do is I have to pull out this one column, these new deaths, into a data frame. So the way I'll do that is like this. If I do this, just death new, then what? Then I just did a series. The way I can do a data frame is I can pass in a list, and I can say some columns here, right? And so it kind of looks weird, right, that I'm putting a list inside of brackets, but that's what's happening. And in this case, I'm really just interested in one thing, which is just, well, how many new deaths were there on this particular day? And so I do that, and I get this nice data frame, which is going to work well for us. And then for my y values, I can just directly pull it out as a series. And that will be death new 2 weeks from now, right? So these will be my x values. That must be a data frame. And then this y values, and this can be a series, right? And in general, why is that? Well, I'm trying to predict one thing, but I might be making that prediction based on multiple columns. So I'm going to head down here, and I'm just going to copy these things. I'm going to copy this right here. And then I'm going to copy this right here, just like that. And I train it. So fit means to train based on the data. So I've given it a bunch of examples of my features and my labels, right? So I can do that, and that's relatively uneventful. And I would like to be able to visualize what it looks like, what this model looks like, kind of what predictions is it making if I have new data. And it turns out that since I'm doing the linear regression on just one column here, it's actually going to be fairly easy to visualize, because I can ask it for a given x value, well, what y value do you predict? So I can do that with this. I can say lr.predict, and then I can have to pass in some sort of value here, right? So I think I can pass in something like, hey, if there's 10 new deaths today, how many do I predict 2 weeks from now? And I have to pass this in as a list of lists, because that was the shape of this up here. And I can see that there's also this array thing, which is a NumPy array. We're not going to worry about that too much for now. The way I'll generally do these predictions is that I might create a data frame that will help me show a fit line, right? That's one way we can represent the relationship here, right? If I drew a line on this, that would tell me for my x variable, well, what do I predict for my y? And so I'm going to create a new fit data frame like this, data frame, and then I'm going to have a column, which will be death new. Remember, that's the number of deaths today. And for that, I'm just going to try to put a bunch of different values, right? Maybe I'll go from like 0 to 500. And let me just take a peek at that. Okay, so that's my death new. And then what I can do is I can actually pass that whole thing in to my prediction to basically figure out what those y values are. So I can say lr.predict. And if I want, I can put in my whole data frame like that and try to find out that column. And again, I get a bunch of these weird values, right, in this NumPy array. But the great thing is that I can say, I want to just shove those things in a new column. And I'm going to call that this. I'm going to say that. And then I might like to say something like predicted, right, to emphasize that this is not real data, it's just a prediction. So I'm going to put this up here. And now when I run this, I can see that I have, for a given number of deaths on today, well, how many do I predict there will be 2 weeks from now, right? So if there's 500 deaths today, I guess I'm predicting that in 2 weeks there's going to be 160 deaths for a particular county. And so what can I do now? I can actually plot this thing. I can say fit df.plot.line, and I can say x equals this thing. And I can say y equals this other thing, just like this. And different models will give you different things, but the linear regression right here that I'm using is trying to give me a straight line, right? So I'm going to run that, and there's some sort of straight line there. And maybe I'll just make it red, because I'm going to soon draw some new points. What I often like to do is after I've have my regression line, I like to compare it to my actual data. And so remember, I had these similar columns before, and that was all in my original data frame. And for my original data frame, I just want to draw a scatter of all those points. And then at this point, I'm not drawing some sort of prediction. I'm actually drawing real data. So I'm going to do that. And I guess it's drawing it down here. Let me actually try to put that on the same one. So I'm going to say AX equals AX. And then I'm going to have the first one return an AX. And then maybe down here, I'll have the alpha be 0.2 again. And why did I put AX there? There we go. And so then I get these nice plots, and I can see that's far too long. Maybe what I should have done is I should have, I can see my data only goes to about 100, so maybe here I'll make my predictions over the range of about 100. And so I'm going to do that, and I can see how that line fits. Okay, well, how well do I do? I mean, I might try to intuit that based by looking at it. And really what I'm looking at is for each of these points, well, I'd hope most of them are near the line, and I can see quite a bit of them are not, right? And so the way we score these things is we'll look at what is the variance in the thing we're trying to predict, right? So what is the variance in this thing? A variance is kind of a measure of how much the values typically differ from the average, right? So I can get my variance, and the variance in this column is 1.35. And the idea is what we're going to do is we're going to say, well, how much do each of these points differ from the average of the points along the y-axis? And then we're going to compare that to like, well, how much do they differ from that red line that I drew, right? If the line is good, then that variance relative to the red line might draw down a lot. I'm sorry, the variance relative to the red line might draw down a lot relative to the average, which I guess I could draw as like a horizontal line. And so the way I can do that is I can come back here, and just like I fit the data, where did I fit the data? I fit it right here. I can check, instead of fitting it, I can score it. Right? And what this is going to tell me is how much of the variance is explained by the model. And that'll typically be a score between 0 and 1, with 0 being the worst and then 1 being the best. And in some kind of weird cases, it can actually go negative, and maybe we'll eventually talk about that. But generally, it's going to be between 0 and 1. And so I see this is not great. Okay, let's try to do it for our other variable that we had as well, right? So I had this one here, and just looking at the plots, I might expect that this one does a little bit better than, I think, what was it, like 9%. So I'm going to copy these things down here, and so I'm going to create a new linear regression object. And then what? Then I'm going to fit it. Where was I fitting before? Here was how I was fitting before. Instead of fitting to the deaths on today, well, let me try to fit to how many, I wanted to get the number of positive cases. Where is it? Let me go up and look at my data frame again. I wanted to fit to the average number of cases over the last 7 days. So I'm going to do that now, right? I'm going to train my model, this new model, based on this other variable. How can I use this to predict how many deaths there will be in 2 weeks? And maybe right away I'm just going to score it as well. So maybe I'll just copy this and then score it. And I can see it's doing quite a bit better. Instead of explaining 9% of the variance, I'm explaining 20% of the variance. If I was explaining 100% of the variance, well, that would be very remarkable because every point would be exactly on that line. Let me try to plot it just like I did before. So I'm going to copy this here. And so I'm going to have this. And then remember that for this fit data frame, I had to generate that up here using a range of values. Right, so I'm going to paste this here. And so what am I going to do again? I'm going to generate values from 0 to 100, and that is telling me, well, what was the positive 7-day average cases, and then I'm going to get a prediction based on that, and then I can plot a line like that. I'm going to do that, and I can see, well, something a little bit weird, right? I guess I guess I didn't change everything, right? I see the x-axis is still how many deaths there were on a day, as opposed to what I'm actually training on, which was the 7-day average, right? So let me fix that and run that again. And so that's a little bit better. I can see that the line doesn't extend very far. That makes sense. Previously, when I was saying, well, how many deaths were there on a given day, the number was relatively small compared to the number of positive COVID cases. And so maybe I'll redo this. Instead of going from 0 to 100, maybe I'll go from 0 to like 900. And so I run that, and I can see this is a better fit. Right now I'm explaining 20% of the variance instead of just 9. So I did something bad here. Well, and I want to talk about that in the next video, but I just want to leave you with a thought. Let's say I'm teaching something in class, and I work out an example. And so maybe everybody sees that example and they try to learn from it. If I put exactly that same answer, or exactly that same example on an exam, what does it mean that somebody does well on that exam? I think there's two possibilities. One is that maybe the person genuinely learned something from that example, and then even though they're seeing the same example again, they understand what's going on. The other possibility is that maybe somebody just memorized the answer to the example, and then when they see it on the exam, well, they just repeat it. And that would be not so great. And so the same thing happens here, right? When I'm fitting, I'm really giving my linear regression model some examples. And then when I'm scoring it, well, I'm actually using those same examples. And so if this score were good, and I guess here it's not great, but if it were good, then I wouldn't really know, well, did the model effectively memorize the answers, or was it overfitting? Overfitting is what we mean when it basically memorizes it. So next time I'm going to talk about how we can actually deal with that problem and get a better sense of whether it's doing a good job. So last time I talked about this issue of basically evaluating our model on the same data we fit it to, right? The model can effectively memorize the answer and look like it is doing well, even if it didn't really learn anything. And so the way we'll deal with this problem is we'll use something in sklearn called a train test split. And this is a general strategy, but this specific method will make it easy for us. And what we'll do is I'll take our original data frame and give us back 2 data frames. We'll train our model to 1 data frame, and then we'll evaluate it on the other one, on the data the model has not seen before. And so it's a better test of whether it's doing well. And so I can see that there's a number of things I can pass into this. One is I can say, well, what ratio of my data would I like to go into my test set. I can say other things like try to stratify the data. Like let's say I was dealing with something categorical, I might want to make sure that I have a similar number of categories on both sides. I'm not trying to do that here, but I will specify a train test set. So let me import this thing. I'm going to say from sklearn import, it's sklearn.model selection, import train test split. Okay, and then I'm going to say train test split. And I'm just going to try to split up my data frame that I have originally. And basically, it's returning something called an array with 2 data frames in it. And so the way I can capture this is I can say, well, I have my train data frame and my test data frame as the order it's going to return them in. And so let me take a look at these. Here's my train data frame. And then here is my test data frame. And you can see that it kind of shuffled things around, right? If I look at the index, and I'm dealing with different data, right? So this is the data frame that my model is going to learn from. And then this other one is the one I'm going to use to actually make sure it learns something. And so I can see right now, if I look at this, there's 6,300 down here and then 19,000 up here. And that's because the default split is 0.25. So I could do something like this if I want, and then that would make this first one bigger and the next one smaller. So I'm going to do that. And then let me just see what I did wrong here. I think I actually have to say test size. So I'm going to say test size equals that. And then this is going to be a little bit bigger, more data to test on, and then a little bit less data to train on. And so there's some trade-offs there. Anyway, now what I'm going to do is I'm going to head back to this example that I had earlier where I was doing my training. And the idea is instead of fitting and scoring on the same data, I'm going to fit to my training data and then score on my test data. So I'm just going to do it again from scratch for review. And I'm going to say LR equals linear regression. And, oh, there we go. And then I'm going to say LR.fit. And I have my train data frame. And then I have a list of columns here. And then here I may have my Y column, right? So that's the general strategy. And then what I want to do is I want to score it, right? And when I'm scoring it, I'm going to give it a Y column and an X column again. I'm sorry, I have to say train DF here. I'm going to give it that same information, but now I'm going to be doing the test data frame. Right, so I'm going to say test data frame, and then same thing down here, test data frame. Right, and then what I'm going to do is, for this, I'm going to pass in a list of columns like before. And what was I doing last time? I was looking at this positive 7-day average, and so I'm going to pass that in, just like that, and the same thing here. And then over here, I can just look at that thing that I'm trying to predict, my Y, which was this thing. I'm going to pass that in, and then the same here. I'm going to do that. And I see that, okay, my score is 0.16, whereas what would happen if I wanted to run it on my original training data frame, like that, training data frame. And here it does better on the data I trained it on, so this suggests that there is some overfitting here, right? The model does better on the data it learned from instead of some new data it hasn't seen before, and so that, of course, is a concern. And so there's different things I can try to do to avoid that, and we'll eventually talk about some of those things this semester. Hello, today I'm going to be talking more about how we can determine whether or not a model is doing a good job or not. How can we interpret different scores and make sure that we aren't getting a good score just by chance. And so I'm going to be picking up last time with the model that's trying to predict COVID deaths 2 weeks out based on the current number of cases. And so let me just quickly review what I did last time. We were doing a train test split on our data frame, and our data frame looked like this right here. And it was per county, and then there's every day in the year there. Then I created this linear regression model, which I imported from sklearn.linear model. And then I did two things with it. I fit it to my training data, and then I scored it on my testing data. And these were the two pieces, my training data and testing data came from here. And so when I was doing this, what I basically did is I put in my Y values, which is what I'm ultimately trying to predict. And then here I put in my X values, or my features, which are things I know right now. So for example, right now I know the 7-day rolling average of positive test cases, and then 2 weeks out I'm trying to predict, well, how many deaths will there be. This can be a single series, which is why we just put a string in the brackets after the data frame. Here we actually have to pass in a full data frame, because in general we might have multiple features. And when I pass in a list to the brackets after a data frame, well, I get a smaller data frame. And that's why I have the double brackets there. So anyway, so I have this 0.2. And we know that the score will be somewhere between 0 and 1. So it's a little bit hard to say how good this score is, right? Maybe you always get something like 0.2 by chance. Do we know? So that's one of the things I want to talk about today. And then the other thing that you might notice is if I rerun this a few times, oh, now I'm at 27%, 32%, 24%, 24, 28, 26. So you can see that based on how I do this train test split, I can get very different numbers, and so that doesn't give us a lot of assurance. So how can we get some more stable numbers out of the system? I'll just give you a kind of a hint of what the problem is. If I look at train DF and I look at this column here, which is the thing we're trying to predict, let me do that. So I have all those numbers there. Let me look at the variance of that column. Variance is just kind of a measure of how different values are from the average. And then I'm also going to do that same thing for the test. And so when I do that for the test, I see that actually they have quite different variances. And if I run this again, well, it's going to randomly shake out differently. Now the test data actually has a higher variance than the training data. And we're going to eventually look at how this scoring function works, but it turns out that it's very much based on this variance, which is why we have such a noisy measure. So let me head over to the slides and try to give a preview of the things we're going to talk about today. We're going to be learning 4 new functions related to model evaluation. So first, we're going to learn these 2 functions here, which will let us score our models. Second, if our model is kind of mediocre like mine is, right? I mean, 0.2 is not great. How can we know if it's not just chance? And then we're going to be using something called the permutation test score for that. And then finally, to get a less noisy measure, we're going to be doing something called cross-value scoring. And so let me start here with these 2 metrics here. I have this R2 score and mean absolute error, and we'll talk about how those work. So if I go back to my slides, or go back to my notebook right here, I'm doing this scoring here. I can also up here, I can say from sklearn.metrics, import, there's a couple things I want to do. I want to do the R2 score, and then the mean absolute error score. And so the way all of these metrics work is kind of like this. I'll call the metrics function, and then I'll say something like, let me actually just check this here quick. I'll say something like, I had to make sure the order is different between my true and my predicted. I'll say, what are the true values, and then my predicted values. And so for example up here, I know that these are my true values, and then my predicted values, well, how do I figure out my predicted values? I can just say, well, model, please predict for me what these y values should be based on these x values that I'm going to give you. All right, so I'm going to do that. And so here I'm putting in x values, and it's going to return back to me y values in this weird array thing that we'll eventually talk about. But I could take this and I could put this right here. And so then I could use lots of different metric functions here. I could, for example, use the R2 score right here, and guess what? It turns out that this score here that's associated with the model is just defaulting to use our R2 score. There's lots of different metrics I could have used instead, but this one is the default one. So let's talk a little bit about how this score is computed. So the idea of it is that this is the thing I'm trying to predict, right? So this is my y column, and so I'm going to say y is here, and I can just peek at that. What I want to do is I want to look at basically the squared residuals of this column relative to the mean. And so what does that mean? So I can take this and I can subtract off the mean of this, and then if I want to, I can square all of that. So this is really a measure of kind of how bad the system is if I add all of these things up. So this is really, well, the variance of the system, except that I'm summing instead of averaging, right? So this was my original kind of total error or variance in the system, I might think of it as, except I'm just adding up, so it's kind of a sum of squares. And then what I want to think about is, what if instead of measuring the distance from each value to the mean, what if I measure the distance to my actual prediction, right? So it'll be very similar here, right? I can say, what is kind of left over if I subtract off my predictions. How do I get my predictions? Well, that's this right here. So I'm going to grab this piece, and I'm going to have my predictions here, and then let me take a look at that. So the way I really think about it is that originally this was how much variance I had in the system, and this is how much I have after I do predictions, rather than just subtracting off the mean. And so what I could do is, well, I could say, well, how much is remaining, right? So I could say leftover divided by the total, and why is that? Oh, let me just put that here. I can say that leftover divided by the total. And I'm like, okay, well, I left 79% of the variance on the table, basically, which means that I took away 20%. And And you can see that that's exactly what this is up here, right? So really, this is the math that people will really kind of use to evaluate how good a regression is. Typically, we can do that more simply with the R2 score, and even more simply, that's the default if I just say linear regression dot score. Let me give you an example of another metric people might use. So maybe I want to just get, well, what is the average error? And so in that case, I would go back to this piece, right? So this is all of the errors. And if I want to get the average, I should probably just think about the absolute error. And then I could take the mean of that, right? So this would be the average absolute error. And it turns out that that is just, rather than me calculating that myself, I could just grab this mean absolute error here. There's lots of different metrics in here, and I think if I hit Shift Tab, well, maybe it's just regular tab, I can see all the different metrics that come here. And most of them I have never used. So I'm going to paste this here, and I see, well, that's kind of strange. It should be the same. It should be the same number. Why is that not the same number? Because I wanted to get the error of my predictions, not relative to the mean. And so, I'm sorry, this was the thing that I wanted to, this is the thing I had wanted to grab, right? So I wanted to say, you know, here are all my errors, take the absolute value of them, right? Some errors are positive or negative. I just want to have the absolute value. Then I have the average. And why is that? Invalid syntax. That usually probably means I have a mismatch in terms of my parentheses. I see. So this one has is matched up there. So I don't know why I grabbed that squared. Okay, so I can see that this is all my errors, and then I'm taking the absolute, and then I'm taking the average. And now thankfully, okay, I will actually get the same thing that I have down here. And so again, right, this is just a shortcut for this kind of more complicated math, but it's another metric. In terms of how these metrics work, this one is kind of counting all errors more equally. You know, error that's twice as big is just twice as bad, because this one up here, where I'm doing the, when I'm doing, where is it? Right here, when I'm doing the R squared score, because that one is squaring my errors, this will tend to make it look worse if I have a few errors that are really big as opposed to many small errors. Okay, so those were a couple metrics, which was one of the things we wanted to answer in the slides. I'm just going to head back here. We talked about our squared score. We talked about mean absolute squared error. And that's our different ways we can measure our errors. The next thing I want to talk about is if our score is kind of mediocre, like 0.2 out of 1, how do I know that that's actually good and it's not just chance? And the answer is that what we'll do is we'll take our original data here, and we'll score it with our model, right? We'll train a model of the x's and the y's and just score. And so let's say my score is 0.8, which is not that good. What I'll do is I'll shuffle around the data so I know that there's no relationship between the y's and the x's, right? So what I'll do is I'll take this y column and just randomly shuffle it. And the word for that is permutate it. And so I get this permutated version of this column, right? You can see that, for example, 5 used to be the first number, and now 5 is down here, right? So I just kind of randomly shuffle that thing, and then I train the model on it, trying to look for the relationship between the y's and the x's, and there should be no relationship, obviously, right? Because I just shuffled everything around, but I can try to train a model and get a score on it. And so if I see that when I'm basically training a model on garbage data, if I get a better score than I did originally, well, that probably means that I didn't have any sort of significant result originally, right? So I probably didn't have any sort of meaningful model. And so that's the rough idea. In actual implementation, what this function here is going to do for us is it's going to shuffle around the data like this, and it's going to get a score, and then it's going to shuffle it again, and it's going to get a score, and it's going to get something like 100 or 1,000 different scores based on these shuffled data. And then based on that, we can estimate and really see this score over here. Is it kind of unusually good, or does it feel like this could fit in with the garbage data? And based on that, we can we can basically say, well, hey, do I trust this model or not? So I'm gonna head over here, back to the notebook, and so maybe I'm just gonna make some notes in here just so it's clear what we're doing. So this part was about metrics, and then this part is going to be about permutation testing. And so I actually already imported it, which is great. So all these things are kind of related to model evaluation, and they're under this thing called model selection, because what we'll often do is have a few different models, and we're trying to have different tools to say, well, what is the model that we think is best that we're going to recommend to people. So I see that I have this permutation test score, and I'm going to paste this right here, and I can see that I need 3 things. At a minimum, I have to have my model, which is just LR. I have to have my my X values, and then finally my Y values. And so the way I'm going to be doing this here is since here I have this test df and for both my X and my Y, I'm just going to grab these, right? So this was my X right here based on the 7-day average. I want to predict this right here. And so I'm going to grab this. And it turns out that this is going to return a tuple of length 3. So I'm just going to run that. That'll take a moment. And the 3 things in that tuple are going to be the score of my model originally. It will be some other scores when I have maybe I'll just call it the garbage score, since I'm permuting the data. I'm not expecting to have any pattern. There's going to be a bunch of those, and then there's going to be something called a p-value. And what the p-value is telling me is, well, what is the probability that a score this good would be generated by a system that's generating all these garbage scores, right? And so if this is really small, then I can see, well, this is actually much better than my garbage scores, and so I actually have a significant result. So since these are the 3 things that it's returning, right, I know that T is a tuple, I can just put that here, and it'll automatically unpack those things for me. So I'll take a look at this, and then I'm going to get a score for my model, and then I can have my garbage scores here. I see there's a whole bunch of them. If I want to, I can put those in a series, and then I can do a histogram of those, and I can see that they're actually around 0 or less, right? All of these, and this was around 0.09, which is actually pretty far over here. So it seems like we're pretty far away from these garbage scores, and therefore this p-value is going to be pretty small. It seems like whatever process I'm using to get all these garbage scores is not likely to have a score this good. So I will take this as a meaningful result. Let me head back here for another idea. So how do we deal with the noise? We saw that when I kept doing it a bunch of times, I was getting different scores. And for that, we're going to use something called a cross-validation score. And the way it'll work is I'm going to split my data, instead of just having these train and test, I'm going to split into 4 pieces. And then each of those 4 pieces are going to take turns being the test data. So maybe first I'll train my data on these rows, and then I'll test it on this. And then my model will get, let's say, a score of 0.2. And then I'll take a different chunk of the data. And each of these are called a fold of the data, by the way. And so I'll train on those first, second, and fourth pieces. So I get a model, and then I evaluate on that test data set, and let's say this time I get a little bit luckier, and it's 0.3. Do it again, 0.1, again 0.2. And then I could take the average of these, and that would be a more stable measurement of kind of how well my model does. It's not kind of as vulnerable to what happens to go in the test or training data set, because all the data at some point is in the test data or the training data. So I'm going to head over here and do this, right? So this is called cross-validation. And let me call this thing, so cross-validation score. And what do I have to pass in here? I have to pass in my estimator, and then I have to pass in my X values and then my Y values. Right, so let me grab those things. Right, so it's actually, I guess, identical to this right here. So I'm going to grab my model, my x values, and my y values. And this time I just want to do it on all my data. So I'm going to say data frame, and then data frame. And actually really what is kind of the best practice is just do that in the training data. And so I'm going to do that. And then I get all of these scores back, right? And the reason is that there were 5 folds by default. So I could say, in this picture right there is 4. Here I see, well, by default there were 5. That's why I got 5 scores. I can say I want 10 of them, and that'd be fine. I get all these 10 scores back. And these kind of look like those numbers we were seeing earlier, like 0.27, 0.17, another 0.27, a 0.304. Right, if I head back here, and I just kind of run this thing a few times, those are the kinds of numbers I'm getting out of it as I randomly split my, my train and my test. So why is this useful? Well, I can have my scores here, and I can say a couple things. I can say scores.mean, and so I can see, well, on average, my R2 score, R squared score is going to be 0.21, but I could also get some sense of the variance, and that'll tell me how sensitive I am to what data happens to end up in the test or training data set. And that probably depends, how much I have some outliers, and how much outliers define what happens with the scoring. Okay, so this will be the way we'll generally do it. And so one last thing, right? When I was showing this picture here, right, I kind of said, well, hey, I have all my data, and then I just split it up into train and test. Why didn't I use all my data here? And the reason is that even though that would have been fine to do in this example, what you're often going to be doing is you're going to be trying to do a few different models. And what you'll want to do is you'll want to do cross-validation on each of the models, and then you'll see, well, one has the best score on average. And you say, well, that one's the winner. That's the one we're going to use in the future. And so there's this risk when you're doing that. Let's say I evaluate 20 models and pick the best one. The best one probably did a little bit better than it should, right? If I do 20 models, some will just by luck do better and some will do worse. And so even though that's the right process to pick the best model, I shouldn't go brag about this cross-validation score, because it wasn't like I was just doing one model as in here. I was doing many models. So what I would do is I'd look at this cross-validation score across each of my models, pick the best one, and then finally would I go back and actually do my real test data, which is still hanging out here. And then that's what I would report as the kind of accuracy of my favorite chosen model. Hello, in this video we're going to be learning about sklearn pipelines. We've been learning how to use linear regression as a model, and often our model will have to transform the data in some sort of way before we can actually analyze it. And so what we'll end up with for our models are these pipelines where we do a series of transformations, and then at the end we'll use an estimator, is what they call it in sklearn, to actually make predictions. And so for this example, I'm going to be using a slightly more complicated data set. In Chicago, right, which is right on Lake Michigan, they have all these sensors on different beaches which are measuring things about the waves. And so we're going to be looking at this data set of all these measurements. So I can see, well, here's an Ohio beach, here's 63rd Street Beach. And then I know all these things about these sensors, like how warm is the water, turbidity, other things like that. And the Y that we're going to try to predict is, well, how big are the waves on this beach? And we're going to be using things like wave period to predict it, or maybe by looking directly at what beach we're on. And so there's some garbage data in here, so I've cleaned that up. So this is a picture of all the data where I have the wave period on the x-axis, and then on the y-axis I have wave height. Then I also try to break it down and to look beach by beach. So here I'm kind of pulling out all the beaches as a sorted list that's unique from the beach name. And then what am I doing down here? I'm drawing each beach separately. So I'm creating some subplots, and I'm looping over those, and I'm basically plotting each beach, right? I'm doing some filtering in Pandas, so I'm plotting each beach in a different AX region. And so I look at this. And so there's a couple observations right away. Often before I do modeling, I like to just do a lot of scatter plots and try to get an intuition for what's going on. One is that I do see that what beach we're on is an important variable. Some of these beaches have different patterns in terms of the waves. The other thing I see is that that the relationship between wave period and wave height is not linear. It's not as if the bigger the wave period, the bigger the wave height, or vice versa. What I see is often there's kind of like this hump in the middle, right? So kind of if we want to get the biggest waves, we need a wave period that's somewhere in the middle. So I'm going to be making 4 different models here that try to analyze this data, and they're each going to be using different variables in different ways. First will be something very similar to what we've done before. I'll try to predict the wave height based on wave period, just using a simple linear regression, and then we'll see what performance we have there. Next, we're going to learn how we can do a polynomial fit, right? So that means if I'm drawing a line on here, well, the line doesn't have to be straight anymore. Finally, I'm going to look at, well, not finally, but next I'm going to look at what beach. If the only thing I know is what beach I'm on, how well can I predict? And then finally, I'm going to look at the combination of both beach and wave period, with wave period being treated as a polynomial, then see how much I can predict there. So in terms of my imports, I have some things that we've done before. The first thing we learned was how to do a linear regression. We would fit our linear regression to a training data set, and then we would evaluate it on a test data set at the very end. Along the way, we might also do cross-validation within just the training data set. So these things are old, and then these things down here are new, right? So in order to be able to deal with this data, and I want in a polynomial way, I might have to transform it using this polynomial features thing. If I want to deal with categorical data, like, well, what beach am I on? That's not a number, right? That's a category. I have to use this thing called one-hot encoder, and if I want to use both of those, I have to use this other thing, make column transformer, to combine them. And in total, what I'm going to do is I'm going to have this pipeline, and in the end of the pipeline, I'm still going to be doing just a simple linear regression, but I'm going to be making all these transformations to the data before it gets to that, and that's how I'm going to be able to do these more complicated models. So let's start down here, and I'm just going to number these 4 models, 1, 2, 3, 4, just following the numbering up here. And so I'm going to have model 1 is going to be just a simple linear regression, like that. And then what I could do is I could say M1, well, actually, I could do different things. I could say M1.fit, and I would fit that to my X values, and then my Y values here. This is uppercase because it's a full data frame, and then this is lowercase because it's just a single series. And I guess before I have to do that, I actually have to separate out my train data frame from my test data frame. I'm going to say train test split df, and maybe I'll just look at the length of both of these. And so about 25% is going to testing, which I'll be fine with that. And so then down here, I have to have my train df, and then here I can put a list of features, and then over here, I'm going to have my train df again, and then I'm just going to have my y column. And so my y column, the thing I'm trying to predict is just, well, the wave height, like that. And then my list of features, well, first off, I've put a list here, and that's why I get these weird double brackets. I'm just going to start with wave period, just like that. And I probably have to capitalize to match what is in my data frame from earlier if I check back. Yep, it looks like all these things are capitalizing. And so I can do that. And now this model has learned the pattern. And so then what I could do is I could say m1.predict based on my testing data. So I could say test df, right? So I give it only x values, and then it's going to predict what these y values are for me. And so let me, why did I call it m2, m1? And so I get all these predictions, and then what I could do is I could compare those predictions to what I actually have for that wave period, right? I can compare these numbers to these numbers down here, and at a glance I see it's not very close. The easier way for me to do that comparison and actually get a score will be, I call this scoring, right? So the score function will automatically call that predict on this, and then it'll compare that to my test df of wave height, and it will tell me what percentage of the variance I'm explaining there. And I see right now it's terrible, right? I'm not really explaining anything. If I just always predicted the average wave height, that would be better than what I'm doing right now. Now, of course, some of this is luck in terms of like how I did my train test split. And so the more reliable way to get a measure here, let me just print that, would be to do my cross-validation. Right, so I can say cross-validation score. And then here I have to give it three things. I have to say, well, what is my model? My model is M1. What are my X values and what are my Y values? I'm going to do this up here. And when I'm doing the cross-validation, I usually do that all within the training data. And I just try to hold back the test data for the very end of my project to have a final analysis. Now I see I actually get a variety of scores, and we can see that, yeah, it is a matter of luck. Sometimes I do worse than 0, most of the time not. I can say how many pieces I want to break my data into. Remember that I cycle through each piece or fold, and it has its turn being the test data set. So I can get more numbers here. Maybe I'm just going to say scores equals that, and I could say scores.mean. And so this is probably a better indication of how well my model is doing. I'm explaining 1/10 of 1% of the pattern, which is not too surprising, right? All I'm using is the wave period, and I'm trying to fit a straight line to this. And I can see, well, yeah, no surprise, I can't fit a straight line to it. Okay, if I wanted to, let me just copy this for a moment. I'm going to delete it shortly. If I wanted to do more columns, that would be an easy thing to do. So for example, if I wanted to also include, let's say like the water temperature, I could easily add that as another column, right? It's very simple to have multiple X values, right? So I can do that here, and then down here as well, and then maybe I get a slightly different score. Still not great, right? Just try to delete this here, right? But it's very easy to add these different things, and why is that? Well, when I do this and I put that list here, I'm just getting a simple data frame of X columns that I want to use for my predictions. Okay. So that's how we can add things. Let's actually think about how we're going to do this now. If I want to have a polynomial fit. So what we'll do is, let me actually delete all of this. I'm just going to create a demo here, which is going to be a copy of my train df. And in my train df, I'm going to have just wave period. Let me take a look at this data frame. What we're going to be doing, if I want to have say like a quadratic fit, I want to just add some columns down here that are going to contain that squared data. And so I could do things like this. I could say demo, I could say period squared equals demo of wave period that, or I could have like one that's cubed like this. And why is that unhappy? Because I'm doing like a comparison, not an assignment, so I just assume that's already exists. And so if I do that, then, and you know what I want to do, I actually want to copy this so that it doesn't complain. I can see what I'll do is that this column, well, 2 squared is 2, 2 cubed is 8, 3 squared is 9, 3 cubed is 27. And so what I can actually do is I can do a linear regression across these things, right? And so even though it's technically a linear regression, it's trying to act like a quadratic or cubic regression because I'm just treating these as regular columns, right? And I can put kind of weights to how important these things are. And so how can I do this? So here I was just manually adding these things. If I want to, I can use this polynomial features thing. And so down here I'm going to say poly equals polynomial features, and I can say poly.fit transform. And what I want to do, I want to transform my data right here. This was what I had before. So I'm going to run this thing, and I see that I get all these different columns. And if I wanted to, let me capture those in data, right? This is one of those NumPy arrays, which we'll eventually learn about. Until we learn about it, I just want to put it in a pandas data frame so I can better see what's happening. So I'm going to say pandas.data frame, and then I'm going to put my data there. And then I want to figure out what the column names are on those, and it turns out that this thing will tell me that as well. So I can say, I'm sorry, poly will tell me that. So I can say poly.lit feature names, just like that. And I actually have to say columns equals that. And now I can see, well, I have x and then x squared, and I actually have to tell what my original name was for that to work. I actually have to have like a list of that, excuse me. And so I can see, okay, well, I have period and I have period squared. And if I wanted to up here, I could say things like, well, I want to have it be a 4th degree, right? So I could have period, period squared, period cubed, period to the 4th. You can see it also is giving me period to the 0th, which is just a column of 1s, right? And so what I'll often do is I'll disable that. It's called the bias column. So I'll say, I don't want that thing. And so now I actually have something that's very similar to what I did above manually. And I could do that with my data, right? I could, if I wanted to, I could do this transformation on both my training data and then my test data, and then that's what I would do all my modeling on. Now, I think to keep things simpler, what we'll want to do is we'll want to automatically transform and then immediately apply the linear regression. And so it turns out that pipelines, which I also imported up here, make that really easy to do, right? So I can create a pipeline down here like this, and maybe I'll just draw this. This is going to be my second model. It's going to be a pipeline, and then we have to pass in a list here. And the way the list works is that I will have like transformers, and I might have like one or more of those. And then at the end, I'm going to have an estimator. Right, so all of these things are going to be modifying my data in some way, maybe adding more columns. And then at the very end, I'm going to actually do my real model. And my real model is just a linear regression, like that. And then here, well, what are my transformers? Well, I'm just going to do polynomial features, like this. And I think degree of 2 will be fine for us for now. And so I have these two things. And then the other detail about this pipeline is that we have to name each of our stages of the pipeline, and the way that it wants us to do that is it wants us to put these things in parentheses to create a tuple, and then put a name as the first part of the tuple. So I'm going to call this transformer poly because it's a polynomial transformer, and then this thing, I don't know, I'll just call that LR for short, right? It doesn't really matter. All right, so let me just take a look here. M2, it kind of shows me all these details of it, but now M2 is just a model, right? And it's a lot like a simple linear regression. I can do it in all the same ways. So for example, if I head back here, all of this stuff I did before, I just created M1 as my model, and I did all this stuff on it. I can do all those same things down here, right? So if I run down here and I just say M2.fit, and maybe I'll just delete this for simplicity, everything's the same. And I can see, well, maybe I'm doing slightly better now, right? So what was my score before? Actually, that's exactly the same. I was expecting to do slightly better. And why wasn't I doing better? Probably because I was evaluating my same model. That's the curse of the copy paste. Okay, so before, let me just see this. I was explaining 0.1%, well, I guess closer to 0.2% of the variance, and now I'm explaining more like 4.6%. So I can see that model 2 is a huge improvement on model 1. And the only thing I really did there, I'm still doing a linear regression, but I'm just giving it a little bit more information to work with by giving it these extra columns. I have a column that says something like wave period squared. And going way back here, the intuition is right, as I'm fitting a line here, and that line doesn't have to be straight anymore. It can be a quadratic line that kind of curves. Okay, so we have two of these models. We have this one, which was terrible, right? It told me almost nothing. Sometimes this one, depending on your trained test data set, would actually lead you farther away from the truth than if you just always guess the average. This one is actually doing somewhat well, right? It's explaining almost 5% of the variance. Let's try the beach and see how we can do that. So that'll be my third model. And so if I come down here, I think for this one, I'm just going to go back to here and try this as a first attempt. Maybe I should have some comments here, right? So this is poly on period, and then what was this one up here? So model 1, this was just linear on period, and then I'm going to try doing linear on beach is what I'm trying to do right now. And so if I have this model, I'm going to call this model 3, and I'm going to delete this again just to keep it clean. I'm going to do this down here. The main thing I want to do is, instead of having it be wave period, I want it to be the beach name. If I had it all the way up here, I just see, well, that's beach name. Okay, so I'm going to head down here, and I want to predict the wave height based on beach name, right? So just like that. And then this is also beach name down here. And this is trying to complain to me. And what does it complain about? It says, could not convert to a float. Ohio street beach is not, it cannot be converted to a float. And that makes a lot of sense, right? So this thing here, if I take a look at it, that's categorical data. And it turns out the linear regression, we'll eventually learn why, but it wants everything to be numeric. And so that's a problem. And so how do I deal with this? I mean, maybe one idea that students sometimes come up with is that I could encode these. I could say, like, 1 means Ohio Beach, and then maybe 2 means Calumet Beach, and then maybe 3 means something like Montrose Beach. And the problem is that if I put these numbers like this, the linear regression model is going to assume they're meaningful. And so what that means is that if the model learns something about Ohio Beach and then it learns something about Montrose Beach, it mistakenly thinks it knows something about Calumet Beach. It's going to think that that's somehow the average of these other two. And of course, that's not true, right? I mean, I kind of arbitrarily put these numbers here. There's no reason to believe that this beach has characteristics that are kind of average of other two. So that's not going to work, right? I can't encode it that way. The idea that we're going to use instead is called one-hot encoding. And one-hot encoding looks like this. One-hot encoder. It's going to be like that. And I can say one-hot encoder.fit transform. I'm going to fit transform this data right here. And I get this weird thing that's, well, whatever is that? That's like it says it's like a sparse matrix. We're going to eventually learn more about that, but I can convert it to this thing, which is a NumPy array, and then that thing I can actually put into, maybe I'm going to simplify this a bit. That thing I can actually put into a data frame, right? So I'm going to say pandas.data frame, just like this. And then just like before, I want to figure out what these columns are. And so just like with the polynomial transformer, I could say get feature names, same deal here, right? I can say one-hot.get feature names, like that, and then I have to tell it, well, what was I originally operating with, and I guess that was like the beach. And why is that unhappy? So the shape of the values passed is this, and the indices imply something like that. I wonder what is going on wrong there. I think my problem is that I need to say like columns equals that. Okay, and so how is this working? So the first one, my first row was Ohio Beach. And you see that I have actually a column for each different beach. And what we'll do is we'll set, within that, we'll set it to 1 if it's an Ohio Beach, and then it'll be 0 in all the others. If I go a few down, I see that I have a Montrose Beach in position 4, right? And so in that case, I'll put a 1 under Montrose Beach, and then a 0 is under others. And that's why we call it one hot, right? So I guess the place where it's hot is where we have a 1, and then everywhere else it's a 0, right? So if I have this, even though I started with some categorical data, I can end up with something where I have a bunch of numbers. And so if I clean this up here, let me go back to this. I'm going to actually delete all of this because this was kind of a dead end, right? What will be a closer inspiration is the pipeline I used before with the polynomial features, because just like polynomial features is a transformer, so also is one-hot encoding, right? So I'm going to tweak this. We're on model 3 now, and this is one-hot, and here I can just blow all this away, and I can say one-hot encoder, just like that, and then I can do my linear regression down here. And so then I can say, down here I can say, I think it was like beach name, right? So beach name, and then Actually, I don't even need this, right? I'm kind of, this will automatically do the fitting for me and tell me how well it's doing. I wonder why this is complaining up here. I get nervous that that's red. Anyway, it'll probably tell me shortly. I can say beach name here. And then let me try that. And then sure enough, it's invalid syntax. Because I didn't have a match there. And so this does even better than before, right? So I guess just looking at the beach name is even better than knowing what the wave period is, right? So my model is getting better and better, right? First I started with just a linear model on the wave period, and then that's terrible, right? I'm not even explaining 1%. Then I said, well, let's do a polynomial fit on the wave period, and I'm explaining almost 5%, and about 4.5%. Then I just look only at the beach, and I get 5.5%. And so the kind of natural next thing to do is, well, let's do the regression on both beach and also polynomial of the wave period. And maybe I can do even better, right? Maybe both of these things are providing me some information. And so here's where I get to have a challenge, right? Because I want to do one-hot encoding on the beach name, and I want to do polynomial features on my other column, right? So I have to have some sort of way of combining these things. And it turns out that that's that last piece that I imported up here. The make column transformer is going to let me stitch together multiple transformers, each of which applies to a different column. So I'm going to come down here, and I'm going to copy this from my inspiration for kind of model 4. All right, so I'm going to have model 4 now. And what am I going to do? So this is what has to change, right? Somehow I have to have something here that can capture both columns, right? Because what I'm going to do down here is I'm going to pass in both beach name and wave period like that in an effort to predict my wave height. And so how do I do that? Well, I'm going to call that thing that I imported, which was make column transformer. And when I'm calling that thing, and when I'm calling that, what I'll do is I'll have just a series of transformers. And so I'll have like transformer 1 and then transformer 2. And if I wanted to, I could have more, but I don't need that in this case. Each of these things, each of these transformers is going to be a tuple, and the tuple will be the transformer, and then it will be a list of the columns that it applies to, right? So both are going to be like this, right? I have these tuples, and maybe I'll just put a new line there. So I'm going to have these two transformers and then a list of columns. And so I think what I want to do is I want to do one-hot encoding on the beach name, right? So I'm going to copy my one-hot encoder right here. And then what column does that apply to? Well, that applies to the beach name column. And then my other one was polynomial features, which I should just copy from up above. That was this thing right here. Polynomial features is my other encoder, and what does that apply to? That only applies to wave period. Okay, so I have this this model 4 now, and then I can, well, try running it, and now I see I'm getting up to 9.5% of variance explained, which is actually, well, I guess I wish I was explaining 100%, but I can see by kind of considering both these factors, I'm explaining quite a bit more than I would have otherwise. So one last thing I want to do before I wrap up this video is I want to talk about why we have these names here. And I can use this. We can use pipelines like a dictionary, right? So for example, that means I can put both here. And what will that give me? That will give me this column transformer that I created right here. And so if I wanted to, I could kind of peek at what this thing is doing as a way to debug my model. I could say fit transform, and then what I could do here is I could say, well, this is the data I'm working with. So I could see that, well, and then I guess I'd actually need to have some column names here as well, but I could see, well, this is what I'm dealing with. So let me do a data frame here. I could see that it has all these columns here that have the one-hot encoding, And then I have these columns here that are doing polynomial features on the other things. So this is the data that I'm using to try to predict what the wave height is. So even though I'm kind of starting with just these two columns, after I do all this transformation, I'm actually giving the linear regression here at the end of my pipeline quite a bit more information to work with, and that's why we're able to do much better here. So as the very last step, what I would like to do, so I saw that model 4 was clearly the best one, right? So that's the one I'll recommend. Now, it's possible if I'm doing 4 different models, one of them just kind of by luck does better, and that's why I hung on to my training data, right? I only used, or on my test data, I only used training data for cross-validation scoring. So at the very, very end, I'm going to fit this data to these things, just like that, and then let me just run that. And then I could use it to make predictions, right? Let me just remember how to do this because it's useful. I could use this to make predictions on my test data frame, like that. I could make all these predictions for what the waves could be. Or I could, as a convenience, score how good those predictions are against my test DF of wave height. And I see, well, now I'm explaining 8.4% of variance, right? So I did get a little bit lucky there, but still, I can say this is clearly better than my other models were. Hello, so when we started learning about machine learning, the first kind of problem we talked about was regression. And after we learned about regression, we learned about some of the linear algebra underlying it. And now we're going to be moving on to a second kind of machine learning problem, which is classification. And so I just want to review the main categories of machine learning. There's 3 main categories. Some people will say 4, but there's reinforcement learning, which is about these multi-stage decisions. We're not doing that in 320. We're really interested in supervised machine learning, which is where we're trying to make some sort of prediction about maybe the future or about some other unknown. And then there's unsupervised, where there's no particular thing that we're trying to predict, but we're looking for some sort of patterns or simplicity within the data. We've been learning about regression, which is where we want to predict a quantity. And so we're going to be learning about the other most common kind of supervised machine learning, which is, well, how do we predict a category? And that's called classification. So just to review these, the 2 differences, here I have a big data frame, and all of these things here are features. And among these features, I have a mix of both quantities and categories. And that's not really relevant looking at my features to figure out what kind of problem this is. When I want to think about what kind of problem I'm dealing with, I'll look at this label. What am I trying to predict? Is that quantitative or categorical? In this case, it's quantitative, so this is a regression problem. And so what will we do? I might have some data up here where both my features and my labels are known, and so I'll fit a model to that, and then I'll use that same model to predict perhaps where that label is unknown, or I might pretend it's unknown so I can basically test the effectiveness of my model, if that's some sort of test data set. A classification problem looks very similar. Again, I might have some mix of quantities or categories as my features. The main difference now is that I have a categorical Y or label column. Otherwise, I'm still going to be fitting my features to my label and then trying to do some sort of prediction on it. So as I've mentioned, right, we have these 4 big categories, and sklearn has so many different algorithms for each of them, or implementations for each of them. And so the one we've learned so far is linear regression. That's what we've been using for regression. So a linear regression model is what we call a regressor. Very confusingly, what we're going to be learning now is called a logistic regression. And it is not a regression. It's actually a classifier, right? So the name says linear regression, but it's a classifier. So don't get confused, right? Even though we're learning linear regression and logistic regression, I am teaching you a regression model and then also a classification model. So I'm going to exit out of here and head over to my notebook to try to introduce this. And let me see here. Here is my notebook. I have some stuff imported. Maybe I'll come back to that later. Let me just jump down here for now. I have this data frame which has some data from a very famous machine learning data set called the iris data set. The idea of the iris data set is that you have all these measurements about iris flowers. So for example, what is the size of the petals? What is the length or width of the sepals, which are I guess like the green leaves between the petals. There are different varieties of irises, so I put the varieties here in this far right column. This whole thing I'm looking at right now is a test data set, and it only has 10 samples in it, which is tiny, right? Normally we'd have a much larger test data set, but I'm just trying to keep it small and simple in this case. I'm passing in this random state so that even though it's somewhat random, I mean, every time I run it, it'll be the same. If I put a different number here, I would get a different random, and I'm using random kind of carefully, order each time. So this is just so I can reproduce it, even though I want something basically random. I want random but reproducible. So I've done that train test split, and I'm just putting 10 here. And so what we're going to be doing is we're going to be fitting different models to the training data, and then just seeing how they act with this very small test data set. And looking at this, there are 3 features I'm going to be interested in. We're going to look at the dimensions of the sepals, and then I have this constant column. Remember that sometimes when you have these models, you could have coefficients in a separate intercept, or you could just have coefficients, and then the last coefficient could be multiplying the one column. And that's what I'm doing here. I think I'll make the later examples a little bit simpler. Those are my features. I actually have multiple y columns here. I'm going to try to see if I can predict different things over here. Can I predict what the petal width is? And I predict whether or not a particular variety is a setosa. There's actually 3 varieties in general, so can I just predict any variety? You can see that whenever I have a setosa here, it's true. For other cases, it's false, right? It's not a setosa. So that's what I'm going to do. I'm going to see if I can predict these 3 different columns based on these 3 different features. I guess it's really like 2 features. And so there's 4 things we're going to do. We're going to do a regression on the petal width, and that's really just kind of review. We're going to do a binary classification on the setosa column. And so we're going to try to predict whether it's true or false. Binary means 2, and so that's why there are just 2 things here. It's either true or false. I'm going to use that same model to not just tell me whether it's true or false. I'm going to ask the model for some sort of probability that it's true and probability that it's false. Rather than just saying, hey, it's true, I'd like to see something like, oh, there's a 95% chance it's true. And then finally, so binary means 2, multi-class means, I guess, more than 2. And so we're going to do that over here, right? You can see I have 3 different categories here, and things get a little bit more complicated in that situation. Okay, so I'm going to head down here, and I am going to first just start with a regression. And so I'm going to say regression equals linear regression. This is just review from before. And I have all these options in here. And this fit intercept one is something I'm actually going to turn to be false. So fit intercept equals false. What this normally does, if it's true, is it would add this ones column for me effectively. When I'm saying false, because, well, I've already done that manually. And that just is going to make my example a little cleaner later on. So I have this thing, and I want to fit it to some data. So I'm going to say regression.fit. And when I fit, what do? I have my x and my y. And then after that, I could do regression.predict on maybe some other x's. And then that would return a y, right? So I'd have something like this. Maybe I'll say like y, y2, and x2. So in my particular example, I have my training and test data. And so what am I trying to predict right now? I'm trying to predict the petal width. Right? So I'm going to copy this column name, and I am going to, when I'm doing my fitting, I'm going to pull that out of my training data. Right? So I'm going to put that in here in quotes. That's my y. And then my x, well, it will be again my training data, and then I have to have like some columns here. I guess a list of columns. And so I actually already created that. Right here I have these x columns. Those are the sepal length, sepal width, and then constant. And so this will be my list that I put inside of here. And so I'll basically get those 3 columns. Let me just So if anybody's having trouble visualizing it, I'm getting just those 3 columns out of my bigger one. Whereas when I'm doing this, I'm going to get a pandas series that contains that petal width column. So I'm trying to predict this based on these 3 things. Okay, so I'm doing that, and now I want to do some predictions down here, and that's going to be the same, right? I'm going to put in X that's basically the same format, except now I'm going to use my test data, and maybe rather than capture that in a variable, just see what it looks like for now. So these are my predictions for what should go in this petal width column. And so if I wanted to, I could maybe even add those into my training data frame, my test data frame, and I could say my prediction equals that, and then I could look at my test data frame. And the thing that it's complaining about is that I'm trying to add some values to a slice of another data set. So when I did this here, right, these are slices of the rows inside of my big data frame. And so it gets confused when I'm trying to add columns to one of these that's not in the original. So it's actually an easy thing to fix. I could just say like test equals test.copy, and then test will be completely detached from my data frame, and I can add columns to it without complaint. So let me run that, and now I can see I have this prediction column over here, and I could go through and see how these predictions are. So I predict 1.3, it's actually 1.2. I predict 1.59, actually 1.4. And so I can see sometimes the predictions are good and sometimes they're, well, not so great. Anyway, that's a regression. That was this part 1 here. Let me go on and try this next piece. I want to do a binary classification on this column right here. And so the code is actually going to be very similar to before. I'm going to head down here. I'm going to change a few things. First off, I want to have a logistic regression. And remember, it is a classifier despite the name, right? So I can deal with a category like this. And then for my Y, I'm going to just have this Setosa column. Is it a Setosa variety or is it not? And so I'm doing that. I'm going to also rename this just so we remember it's a classifier. I'm going to call it CLS. Then down here I also need CLS. And I do that. And now I can see my predictions here. I can see that this column is telling me what the flower actually is. And this column over here is telling me what the model predicts it is. And actually, I guess we're doing quite well here, right? Every one of our predictions is completely accurate, which is great. All right, let me go back up here to the different things we want to do. So we did the regression using linear regression. We did the binary classification using logistic regression. And then basically saying, well, do I have a true or false? Now what I'd actually like to do is know, well, what is the probability of getting a true? And so I can do that like this. I can say, this has an extra function. It's very similar to the predict, but it'll be like this. It'll be predict probability A. And I'm going to get a NumPy array of all the probabilities. And so what this means is, the way I'd interpret this is that there's a 94% chance of false and a 5% chance of true. And that's why it ultimately reduced that to a false. 97.9% chance of false and only a 2% chance of true. That's why I get another false. Let me look at this one. This one had about 93% chance of being true, which is why I have true there. And so I could even, if I wanted to, I could try to pull out that last column. I could say something like, I want to have some sort of slice. Remember, I have like a row slice and then a column slice when I'm doing this. I want all the rows and I want that second column. These are just the probabilities of it being true. And so if I wanted to, I could say something like test of probability equals that, and then I could look at it again. And I can kind of see in each case, well, based on these dimensions, what probability does the model think it has of being a Setosa? And so sometimes it's not quite sure, right? Based on this, I could identify the cases where the model was not very confident, and then I could identify other cases where it was quite obvious what it was. So I don't have to do a new model for that. I just have to call predict probability A instead of predict. And okay, so let me head up here. And we're going to do this last piece now. How can I do a multi-class classification on variety? And variety is a little bit trickier because I have 3 different categories there. I guess it's going to be trickier when we actually get into the math behind it, but it is not trickier in terms of actually running the code. So if I actually copy this here, and then I head down here, I'm just going to call this multi, so I can remember my 3 different models. I'm going to say multi, and then what else do I need to change? I'm doing a different column this time, and so I can do that. And now what? It's going to tell me for my predictions. It's saying my predictions are still false and true, and that came from here. And so this is returning true and false because, well, my new model is called multi, and I'm using my old model. I'm going to do that, and now I can see, while we're writing that, I can see, well, what does it predict for this one? That one it got right, that one it got right. Here it actually made a mistake, right? Models make mistakes. That's not surprising. I guess that was the only mistake in this data set. And then, of course, this probability column was from earlier, right? So I'm just going to ignore that because I keep on writing this probability or this prediction column for each of my 4 examples. Okay, so there we've seen a few different things, right? We've seen a regression, and then we've seen these 2 different kinds of classifications. Let's try to get into the linear algebra behind each of these examples. And so I'm going to head down here. And remember that I had REG, that was my model earlier. And inside of here I have coefficient, and I also have intercept. And the intercept is 0 because earlier what happened, I passed in fit intercept equals false to all of these. If I had not done that, then what would have happened? Then my coefficients, I only had these 2 columns here, or 2 numbers here, corresponding to the weights on these 2 columns. And then instead of this being basically my intercept, that would have gone to the separate variable down here instead of being here. So basically, these are my weights on my real columns, and then this is the intercept, or the weight on my ones column. Okay, so I have that thing, and what I'd like to do is reshape it so that it can be, I want it to be however many rows necessary and then 1 column, so it'll be vertical like that. The other thing I want to do is I want to get my x data, which will be my test data frame, and then it'll be those x columns, and maybe I'll say dot values, and so I'll look at that. So I'm pulling those first 3 columns out of here. Okay, so I have 3 columns here, and then the column over here is basically 3 entries in it. And so if I wanted to, I could take the dot product of this with these down here, and that's exactly how linear regression does predictions. So if I come down here, so I can say define regression predict, and if I have some x values here, what I could do is I could return x dot, basically these things, right? So I could say, maybe I'll call this like vector 1, or I'll call it coefficient. You know what, I'm just going to actually, why not just put it here directly? I don't need a separate variable for that. And so I'm going to look at this regression predict, and I'm going to do it on my x data, and I get these predictions, 1.32, 1.59. Let me actually draw up here earlier, and I see that those are exactly the predictions that my linear regression made earlier, 1.32, 1.59, right? So this regular regression.predict, like this, all it's doing is this right here. It's doing this math right like this. Okay, let's try to see what the logistic regression is doing. So it's actually going to be very similar. So remember before, what was I doing? I was saying CLS, my classifier.predict, and I can just do that. These were the values I was getting out of my classifier. What math is this doing? It's actually almost identical to this. let me copy this. In fact, I'm just trying to tweak it very slightly. I'm going to have my CLS predict, and then I'm going to say CLS predict, and my X data, and the difference, right? I have all these numbers now, and actually, sorry, I want my coefficients from my other one, so my CLS coefficients. I should look at those as well before I jump into this. I'm going to have different coefficients. I'm like, oh, why are all the numbers the same? That doesn't make sense. And I get all these numbers. And remember, our goal is to predict false, false, or true, or things like that. And so the way it works is that we're getting a score for each entry. And if the score is greater than 0, we predict true, otherwise we predict false. And so the shape is a little bit different here. Maybe I can just reshape so it's more obvious. But otherwise, that's what it's doing. All these numbers up here are the same down here. And I think maybe this is why they even call this logistic regression, even though it's a classifier. The math is basically identical to what we have for a linear regression, right? At the heart of it, we're just doing a dot product. The only difference between the linear regression that we did before and the logistic regression we're doing now is we're just checking if some number is greater than 0. Okay, so let's do this next piece, right? So the next piece was, I'm kind of going back through my examples before. After we did predict, which was trying to say, well, are we predicting true or false? We wanted to get this probability. What is a probability that's a setosa? And so how can we get a probability out of this? If I head back down here, you actually see that before I added this greater than, I had a numeric score. So I'm going to go back to that. And I'm going to say I want to predict probability A now. I'm just going to go back to this. And predict my probability. And I'm going to do that. And I see I have all these scores. And of course, these are not probabilities because a probability would be between 0 and 1. But it turns out there's a very simple function that can turn it into a probability. And that function is called the sigmoid function. And I had it at the beginning of the notebook, but I haven't talked about it yet. I'm just going to head up briefly, and we're going to talk about the sigmoid function and how we're going to use it. We don't have to go into a lot of the details on the math. I don't care if you remember that. I certainly don't remember it. The important thing for it is that the x value that's going in can be as large or as small as we want. But if I get very, very negative numbers, I effectively approach 0. And if I get very large numbers, I effectively approach 1. So the nice thing is that I could take any sort of numeric score in, and it's going to give me back a result between 0 and 1. So basically I can take some other sort of score and turn it into something that at least looks like a probability. And so what I'm going to do is I'm going to call this sigmoid function down here, right? And so instead of having all these numbers like negative 2.76 or 2.57, I'm just going to take the sigmoid of all of those things, and then they will be these numbers all between 0 and 1. And it turns out that that's how we would actually be doing the probabilities, right? So just like before, I was trying to say, well, predict the category on X the same way down here. If I maybe I'll do this right here above. I'm going to say predict the probability of A. Let me just look at what's happening here. These numbers right here, which is the probability of it being true, is this column right here, the probability of it being true. The way I've written this code, I'm not computing the probability of it being false because, well, that's boring, right? I mean, they add up to 1, so why would I do both of them? But you can see these numbers here are exactly identical to this down here, right? So getting the probability is very simple, right? I'm still just doing that core dot product, and then I'm just applying the sigmoid to every number inside of the result, right? So we've seen for all these cases so far, this dot product is just extremely important, right? I'm taking the dot product of a matrix with a vertical vector. Let me go up and talk about the fourth model we did with a multi-class model. The multi-class model was right here, and I was trying to predict variety. And variety could be any one of these three things. And what it's going to turn out is that my coefficients for variety are going to be a lot more complicated. So if I look at, so this is my binary one. If I look at the coefficients for my binary one, I just have these three numbers. But if I look at my coefficients for my multi-class regression, I actually have not a vector, but a whole matrix with all of these numbers in it. And so let me use these now. And what we're going to do is actually, I think, just like the way they set it up, we're going to have to transpose them. We're going to do that. And let me grab this here. It's going to be very similar again, but instead of multiplying x by just a vertical vector, I am going to multiply it by this whole thing right here. We multiply it by that whole thing, and then I get this result. And so I'm going to just call this quickly. I'm sorry, this is multi-predict now. Multi-predict. And I'm going to call that multi-predict of x. And I'm actually not doing sigmoid anymore at this point. My apologies. And so how do I interpret this? Basically, every one of these columns corresponds to one of the three varieties. If I had had more varieties, I would have had more columns up here, but I would have still had 3 rows in this coefficient matrix. Right, so you might imagine, I don't know which one is which, but you might imagine that this is the Setosa variety. And it turns out when I take my big matrix of data and I multiply it by all of these columns right here, what it really does is it goes column by column. It takes this column times my data matrix, and it uses that to produce this output column. So these might be the scores for how much it looks like a Setosa. And then maybe let's say these are the coefficients for a versicolor. Then these would be the scores for a versicolor. If these were the coefficients for a virginica, then these might be the scores for the virginica. And so what I can do is that each one of these rows corresponds to a row in my original data, which means this row corresponds to one particular flower, one particular iris. And so for that one particular iris, I have a score. How much is it like a Setosa? How much is it like a versicolor? How much is it like a virginica? And so what I can do is I can try to take these and I can see which score is the highest. And in this case, it's this middle one. So whatever type of iris corresponds to that middle column is what I'd want to predict. And so I can check that. I could say, if I go back to this, I could say, I think it's classes. I could see, okay, well, this, I guess, well, this is the Setosa, and so that first one would be a versicolor, right? And so one of the ways I could actually do this is there's a, it turns out that there is an ARDmin call. Let me just try to do this here and make sure I get it right. I am getting it right. Okay. And so what, or I guess I want argmax. What this is going to do is it's going to give me which index is basically giving me the largest value. But I have to specify what axis. And 0 is down and 1 is across. So I'm going to say 1. And what is this telling me? I'm going to reshape it so it's a little bit more obvious. I'm going to say negative 1, 1. What this means is that at index 1, I have the biggest number in that first place. The second position, the biggest number is here. Is that true? Yeah, that's true. This number is bigger than those other ones. Let me check the fourth one. That means the 0th position is bigger. So this is bigger than these. So it's absolutely true. And so what's cool about if I have a NumPy array like this, I can put that into another NumPy array like this. So I can take these classes and I can put this array of numbers into here. And I'm going to get basically, well, what are all these categories? And so I'm going to take all of this and I'm going to put it back in here. And I can see that then I'm going to get the predictions for all my for all of my flowers, right? I can see for each of them, well, what am I predicting it is? right? And this will correspond with my predictions earlier, right? So again, dot product is at the heart of it. But now, since I have different possible classes, I have to have coefficients to get a score for each class. And so that's why we have to multiply the data by a full matrix instead of just a vector. And that's the first example we've seen like that, a real practical use case in this course. Hello, in this video I want to talk about how we can visualize the decisions or predictions that are made by a classifier. When we were doing regressions, we'd often visualize this by drawing a fit line. And the equivalent here is that we'll often, at least when we have two features, is we'll draw those two features on an x and y axis. And then we'll separate the area into two different regions, one where we predict true and another area where we predict false. And so the function that we'll be using in Matplotlib is called contourf, and it can do that kind of plot. So we want to evaluate CLS, and the idea is that we want to put in a bunch of different values for both sepal length, which I'm going to put on the y-axis, and sepal width, which I'll put on the x-axis. And so the way to get every combination of these, maybe most easily, is with a NumPy mesh grid. And the reason I'm using a mesh grid is that it creates some arrays with different combinations in exactly the form that I'm going to need later. So creates arrays and form needed for contourf later. And so maybe I should leave this comment here like that. And what is it trying to return? Well, it's trying to return two arrays. It's trying to return one, which is one of my variables, and the other one will be the other variable. So maybe I'll say I'll put my sepal width first, and then my sepal length, just like that. And then what I have to do here is I have to have a range, right? So I'll have like range 1 and range 2. And really what the mesh grid is going to do is it's going to give me every combination of these two ranges. So here I'll say NP a range, maybe I'll go from 0 to 0 to 10, and maybe do a 0.1 step. And then the same thing over here as well. Okay, so I have those two. And let me just take a look at what these things look like. I see that both of these are a 2x2 matrix that are showing me every combination. So let me look at the other one as well. So these are exactly the same shape, and the values in it are just giving you the coordinates, right? So the first one is giving me the x coordinate, basically, the sepal width, and the other one is going to give me the y coordinate, or the sepal length. And so if I wanted to, I could then call plt.contourf, and this is taking three things. It has to have my matrix of my x coordinates, and it has to have my matrix of my y coordinates, and then it has to have something that says that gives the color, right? And that can be some sort of kind of expression, right? So I could say, if I wanted to, sepal w, and this will show me some stripes from left to right, or I could do sepal l, and that'll show me vertical, or I could have some sort of mathematical expression, right, like this. And at each point, it's showing me, well, what would happen if I multiplied the value in one of these by the value in the other, so I can get these nice contour maps. Now, what I'd really like to do is to just have two levels, two numbers. Maybe let me just show you what this is now. Lots of different numbers. I'd like to just have two numbers here, basically 1 and a 0, that correspond to predictions, right? So it'll be, my x-axis is going to be the sepal width, and my y-axis will be the sepal length. So I have to get all of this data into a format where I can do some predictions, right? So let me leave this here for now, and I'm going to come back to this. This is my goal where I'm working towards. What I would like to do is put these things in a data frame. So I'm going to say this will be my contour data frame. I'm going to say pd.data frame, and my data frame has to have all of these things up here, right? Because I want to do predictions on it, and these are my x columns, and so I'm going to have something for that. I'm going to have something for that, and then I'll do my constant first. That's easy. That's just 1. These values I can pull from these, and so I can put this here, and then I could put up here, I could put sep w if I wanted to. Now this is not going to quite work because these are those basically square matrices. And down here, I'm trying to put all this in a data frame so I can do my predictions. It has to just be a simple column. So I have to flatten these. So it's just kind of one-dimensional. And I can do that, and then I can look at my CDF if I like. And I can see what is going on here is I really have every combination of length and width, and then I have my constant column. So this isn't a great format for me to then do some predictions, because I can just say it has everything that I need for my predictor, right? I could say cls.predict, just like that. And then I get all of these values right here. And if I wanted to, I could add those to that data frame as well. I could say CDF. I could say predicted. Maybe I'll just say prediction. And I remember that was the petal width is what I'm trying to predict. I can say, or I'm sorry, it was the category. Is it setosa or not? Right? So that's what I'm trying to do. Okay, so I have that, and now I'd like to be going down and doing my contour plot down here, right? So I can have this, and let me think a little bit carefully here, right? So if I have my sep w, let me look at the shape of these. That's a 100 by 100, because that's what my range was. I was drawing over 100 numbers. This is a 100 by 100 matrix. This is a 100 by 100 matrix. This is also going to have to be a 100 by 100 matrix. Right now it's just this long column. So just like I had to convert these matrices to columns with a reshape here, now I have to go in the opposite direction. I have to take values and then reshape this to be matching the format of these, right? So I can actually just use these and say, well, my prediction should be whatever shape my x values are. And so that'll line up nicely. And so I can do that, and now I can see, well, the two sides of this are going to correspond to a prediction of it being either a setosa or not a setosa. Let me plot those with a scatter plot on top of here. I have my data frame here of all my original flowers. I'm going to plot all of them. Ideally, I would just plot only the training data on top of this, so I can actually have a better sense of what errors are made. But I only have like 10 rows of my testing data, and so I'm just going to plot the whole thing. So I'm going to say .plot.scatter, and actually what I'd like to do is I'd like to just separate this out. So I'm going to have something like setosa .plot.scatter, and then I'm going to have something like other.plot.scatter, and then those things I can get just with some filtering. Right? So I'm going to say setosa equals data frame, where data frame of variety equals setosa. And then my other ones will be basically where it's not that. So I'll say where it is not setosa. Okay, so what am I going to do down here? Well, I'm going to say my x value is going to be, well, I was putting sepal width there, so I better put that sepal width on my x-axis. And then my y-axis should be sepal length. Okay, so I'm going to do that, and then I'm going to do the same thing down here for a moment. And I see, okay, well, I have my decision boundaries, and then I have my two separate plots down here. I'd like these to all be on the same plot. And normally, the way that we've done things like that is we would say AX equals this, and then we'd pass that down below. Let me just show you quickly what the type of AX would be if I were to do that. It's this thing here, this quad contour set, and we cannot plot on top of that. So if I wanted to reuse the same axis subplot area, what I can actually do is I can say matplotlib.get current axis, and that will give me an axis subplot that I can pass in elsewhere. Right, so I could say up here, I could say, maybe I'll go on to the next line. I could say AX equals that, and same thing here. So then they'll all go to the same area. So let me do that. And so I have all of these points, and And so then what I like to do now is, well, it's kind of strange that it's not overlapping that boundary. Did I get my axes mixed up? I did. So here was sepal width, sepal length. Okay, great. So let me just switch this back. So this should have been sepal length, and this should have been sepal width. And now I can actually see that makes a lot more sense. I can try to separate the ones that are from the ones that are not. And so to actually make this work now, I should have the color be different in some way. So I'm going to have the setosas be red, and then maybe I'll have the other ones be, I don't know, maybe they can be gray. Right, so just like that. And so now I can start to see what mistakes will be made. I can see that there's one setosa that is not going to be recognized as a setosa because it's on the wrong side of this boundary. I should probably also have some labels here. So I'm going to say like label equals setosa, and then down here maybe I'll say label equals other, just like that. And so I can see what's happening here now. And so there's a couple steps to all of this, right? Maybe I can delete these extra things up here so I can have a minimal example. I had to create a mesh grid, and that basically for every point, one grid had the x values, and the other one had the y values. I had to reshape those to convert them to data frame columns, and at that point I really had every combination of these in some row. Once I did that, I could add predictions for basically every combination. And then if I converted my predictions back to the mesh grid format like these two have, then I could do my contour, and that's how I could create this map. And then on top of that, I could plot my scatter points and see what's happening. One last thing I want to do here, and that is I want to try to do some polynomial fits. So just like we can use polynomial features for a regular regression, I can use those for classification as well. And so let me import some stuff. I'm going to say from sklearn dot pipeline import pipeline, and I'm going to say from sklearn dot preprocessing, I'm going to say import polynomial features. Okay, and so before, what did I have? I had I just had a logistic regression like this with what was it? It was I'm just trying to search up in my page for earlier. I think it was this fit intercept thing that I had off for all of them. Excuse me. So I had that. This is my model before, and that's going to be part of a pipeline, right? So now I'm going to say pipe equals pipeline, and the pipeline is going to be this list of stages, just like this. And so that'll be the first stage. Well, sorry, that'll be the last stage. And then before that, I want to have my polynomial features, just like that. And then the other trick is that each stage of my pipeline has to be a tuple. And the reason it has to be a tuple is because I have to give it a name, right? So I guess I'll just call this poly, and I'll call this one LR. So I have that and it's straight. And so just like before, I could have my, I think before I had something like this, fit, and then I had train of X columns, and then train of, what was my Y column? I guess it was going to be my petal width, I think. So let me just copy that. It was like this, but it was petal width. That's what I was doing before, and I can just replace my logistic regression with this pipe. So let me try that, and I get some sort of error here. Unknown label type continuous. Oh, I'm sorry. I'm trying to predict whether or not it's a setosa, right? It's complaining because it's continuous. So it's saying, hey, you're trying to do a classification on a quantity, which we don't do classifications on quantity. We do regressions on quantities. So what I'm going to say here is setosa. Is it a setosa? That's what I care about. And then I train it, and that's all great. Now, if I want to, I can come back here and I can repeat these steps, right? So I could, if I wanted to, maybe I'm just going to move all of this up here. And then when I'm plotting this, when I want to look at those decision boundaries, instead of using my simple classifier before, I could use my pipeline classifier. And then what's going to happen? Well, that boundary line between them is just slightly more curved. It doesn't quite help. That red point is still on the wrong side. But you can see I can get different shapes depending on the complexity of my model and what I have in the pipeline beforehand. Hello, in this video I may be talking a little bit about how we can score our models on our training data. And scoring them is going to involve learning some new metrics and terminology. It turns out there's different kinds of errors, and if sometimes we'll care more about one kind of error than another, we might want to use different metrics to deal with that case. So for this, I have some really simple dummy data. Basically, I have this data frame that has an X column, and the X column is a number, and then the Y column is a Boolean, and it's true whenever X is positive and false when it's negative. Okay, so not much data there. And just for simplicity, I'm kind of breaking it into the first half and the second half. I wouldn't normally do this, right? Because maybe the data is not shuffled, and maybe I'm kind of getting very different data in the two halves. So this is just trying for an example. So there I have it. I have my training data and my test data down here. And if I want to try to figure out what is the relationship between Y and X, and then measure the model's understanding of that relationship, I'm going to use some sort of scoring function, right? So I'm going to do this with a logistic regression. Remember, this is not really a regression, it's actually a classifier, right? Because I have this categorical data that I'm trying to predict. And so I'm going to train one of those, and then I want to score it. So first step, right, is I'm going to say LR equals logistic regression, right? And then I'm going to say LR.fit. And when I'm fitting, let me actually just try to run this. Once I run it, I can actually hit Shift-Tab and get a hint. I have to give it the X data and the Y data. And so I'm going to give it both those things from the training data first. And so I'm going to say training data, and then the columns I want are just X. And then the thing I'm trying to predict is just the Y value, just like that. And then after I do that, I can basically run a command that's very similar, and that command is score. I can evaluate how well it does on the test data. And I get 0.75. So what is this score function doing? It turns out it's a shortcut, and I'm just going to show you a little bit in the documentation what it's doing. If I head over here, I see that the score function for the logistic regression is giving me the mean accuracy. And if you look at other estimators, they might be doing other kinds of, using other metrics for the scoring. Okay, so mean accuracy, so that's the default here, but it turns out there's lots of different metrics we could use. And so if I go to the metrics page for sklearn, I can see that, hey, there's a whole bunch of metrics here related to classification, clustering, which we haven't talked about yet, and then a whole bunch related to regression as well. And so the one I'm using right now, the default, is that accuracy score, right? You saw that, how it's saying here that we're just getting the accuracy, and accuracy is very simple. It's, well, what percentage of the times did we get it right? And so I certainly could have, instead of using that score function, I could have used this one myself. And I think that's a good thing to do right now, because once you understand how to use this manually without the shortcut, then we'll understand how to use these other functions as well. Okay, so I can see this is in the metrics submodule. And so when I head back here, I'm going to do this. I'm going to say, and this was that page I was just on, I am going to say from sklearn.metrics import accuracy score. Okay, and let me just run that. And when I call accuracy score, I hit Shift Tab here. Basically what I'm doing is I'm saying, well, what are the true values, and what did my model predict? Okay, and so there's different ways I could do that. I mean, I could say, well, the true values are A and B, but I actually predicted A and C, and it turns out if I do that, well, I'm just 50% right? So this was my actual values and my predicted values. So let me actually try to get these from up above, right? So before I was trying this score thing, and then I was trying to give me my x values and my y values, and so I'm going to pull pieces from this. The first piece I'm going to do is I'm going to actually figure out what the predicted values are. So those are going to be the predicted values, and I actually have to call predict here instead of score, right? When I'm predicting, I'm not giving it any y values, right? Predict tells me what the y values are. And then I also have to have my actual, right? And my actual was just the second piece from before on that column. So maybe actually let me just do this. I'm going to say, let me look at the actual values and the predicted values as a list. Okay, and I can see the actual were true, true, false, false. But I'm actually getting true, false, false, false. And so the second one is the error, right? So I'm going to be wrong 25% of the time. And so accuracy is actually going to be 75%, which is what we saw before. And we're going to see it here too when we actually pass in these two things. I pass in the actual values and those predicted values. Right, so I'm going to get that 75%. Okay, now, so that works fine, but there's going to be cases where we don't want to just know how often we're right, but we want to know about, about what kind of mistakes we're making, right? So, for example, let's imagine different things that this y column might be. Let's say that this y column means it's a good investment. Maybe it's for a stock or something. I don't need to know about every good investment, but if I have some system that kind of tells me like, hey, these are some good investments and it's always right, and it doesn't tell me about every good investment, that's a pretty good system. In contrast, maybe this is telling me, I don't know, is somebody contagious for COVID-19 or whatever, right? And in that case, it's much safer to make the mistake of saying they are contagious even though they're not. So there's different kinds of errors, false positives and false negatives. And so there's a lot of metrics based on that. And the simplest place to start is with something called a confusion matrix. And a confusion matrix shows the categories that things actually are, and then how they mistakenly get classified as other things. And so just like before, just like we have an actual and a predicted list, when we have a confusion matrix, we're going to do the same thing. So imagine I had pictures of animals, and I had 4 dogs, 3 cats, and 2 mice. And but then I have some machine learning system that's looking at those pictures and is maybe predicting these other things. What I could do is I could create a confusion matrix using sklearn, right? This is also under metrics, just like accuracy score. And so I can create one of these, and just like with the accuracy score, I can put the true values and then the predicted values, just like that. So I'm going to say actual and predicted. And this is a little bit confusing because each one of these values is kind of showing us how many categories fall into like a specific actual category and a predicted category. And it's not really clear to line it up, right? Well, is this first row dog or is it cat? And so what people will often do, right, is that they'll say labels like this. And just to control the order. So for example, maybe I want to say like cat, dog, mouse, just like that. And then if I pass in these labels, it's going to be a little bit different, right? Whereas if I say dog, cat, you can see these numbers switched a little. And another reason for this, besides just controlling the order, right, so that makes sense, is that I could, maybe there's things that I know exist but didn't even show up in the data, right? There's no horses, right? So let me actually really kind of talk about what these numbers mean. I think it'll be a little easier to put in a data frame. And so I'm going to put this in a confusion matrix here. And now let me put this in a data frame. pd.dataframe, confusion matrix. And when I'm creating a data frame from this, both the index and column labels are going to be the same, right? So I'm going to have it just be like this. And so when I'm looking at this confusion matrix, what does it mean? So the row means what it actually is, and the column is going to be what it got classified as. Right, so I can see in this, right, that there's 4 dogs, and of those 4 dogs, it correctly classified 3 of them as dogs, but one of the dogs was mistakenly identified as a cat. Okay, it looks like there are 3 cats in the system. 2 of them were correctly identified as cats, and 1 was considered a dog. And then I can see other things here, like, well, the system's really good at mice, right? It always correctly calls the mice and doesn't mix them up with anything. And so this is useful, right? When I have a list matrix, I can see what ways the classifier is confused. Hence, it's called a confusion matrix, right? It's showing me how the model is confused, right? So hopefully that's helpful. Now, it's very common that we'll be having these confusion matrices where the classes, instead of being, different animals, it might just be true and false. That would be for a binary classifier where I just have these true and false values. And so let me actually go back to what I had before, right, when I was computing this accuracy score. And let me create a confusion matrix here. And maybe I'm just going to copy some of this down here. I'm just going to grab this. And in this case, the labels are false and true. And it doesn't do anything. Okay, so I have these different categories. And just like before, I think it's going to be helpful to put this in a data frame, right? I'm going to put a data frame here just like that. And so here, again, the row is telling me what it actually is. And then the column is telling me how those got classified. And ideally, in a perfect world, right, everything will be on the diagonal, right? That means there were no mistakes made. There was no confusion. Okay, so I have that. And it turns out there's special names for each of these 4 values. And so I'm just going to go through this quickly. The top left one, actually, let's start with the bottom right. So if I go to, let me put this in a actual data frame. So that's going to be my confusion matrix as a data frame now. Okay, and if I go iloc 1, 1, that's going to be that bottom right. That's going to be called true positives. And you're in practice trying to remembering these words. They're important terminology, right? So I'm going to do this. And then if I had been smart with this example, I would have made sure all these numbers were different so we could more easily identify, right? And then the other numbers on the top left, and those are true negatives, right? So true means that the model is doing the correct thing, right? So in this case, I have one. You know what I should really do is I should do it like this: true positives, true negatives, right? People often abbreviate it this way. And then there's the mistakes, right? The mistakes are false, right? So I'm going to say false and false. And so what are these called? The false positives. Well, where are those? So false positive means that in this column, right? And so it should be false, right? That's what it actually is in the data. But it gets classified as true, right? So what does that mean? That means I'm in row 0, column 1, and then the opposite down here, right? Sometimes it actually is true, but the model says it's false. That's a false negative, and false negative, just like that. Right, so these are the 4 different cases I'd have. And a lot of the statistics we're going to be looking at in the next video are combinations of these, and I'll be kind of talking more about why those are meaningful. In the last video, we learned a little bit about confusion matrices. And confusion matrices give you the whole picture, but often we want to summarize things in just 1 or 2 numbers. And one of those most important numbers, which we've already seen, is accuracy. Accuracy tells us what percentage of the time our model is correct. And but when it gets it wrong, it doesn't really tell us what kind of mistakes are being made. And so we're going to be learning 2 metrics, recall and precision. which really you can think of as accuracy on a subset of the data, right? So there's still going to be fractions between 0 and 1, and but they'll kind of help us pinpoint where the mistakes are actually being made. Okay, so to review, here's a confusion matrix. Along the rows, I have what the data actually is. And along the columns, I have what the model thinks it is. And so right now, I have zeros in all these places. But if I were to see an actual mouse, and the model predicted that it's a mouse, then I would go to the mouse row and the mouse column and increment that number by 1. Right, and that's good. Anytime we're incrementing numbers on the diagonal for confusion matrix, that means we made the right decision. Here's an example of a wrong decision. If our model took a look at that picture, which is clearly a dog, and need of some grooming, and it predicted it's a cat, then we go to the dog row because it's actually a dog, and the cat column because that's what was predicted, and increment that. And so we might do this over our whole data set, and we have a bunch of numbers there. Now, from that, we might want to figure out what the accuracy is. And the accuracy is, well, what percentage of the times were we correct? And so the way I think of that is adding up all the numbers on the diagonal. That's how many we got correct. And then dividing by all the numbers in the matrix. Right? So then look at 8 over 10 or 80%. And some observations here is that this number is a fraction of kind of a subset over a larger amount. It's always going to be between 0 and 1. And the good number is always in the numerator for accuracy, so 1 is the best possible number. And so precision and recall have those same properties, but they're going to be on different subsets of the matrix, right? We aren't going to be taking the whole diagonal divided by the whole matrix. So precision and recall, it turns out we can actually have these metrics for each class, right? So I'm actually going to have 6 different metrics here. I have dog recall, cat recall, mouse recall, and then similar dog precision, cat precision, and mouse precision. And so I'm just going to look at a few of these. So when I'm asking, well, what is the cat recall? What I want to know is when we actually have a cat, what percentage of the time is the model right? And so since I'm asking about what is actually the case, what I'm really doing is I'm dividing by the sum of numbers in a row, right? Because each row represents what the data actually is. So in this case, right, so the denominator will be the sum of the row, and the numerator will just be a single number, which is cat. How many times do we actually call a cat a cat? So in this case, we'll get 2 over 4. And so this is actually one easier way to remember recall versus precision, is because recall has an R and row also has an R. If I'm looking at dog recall, okay, so when we actually have a dog, what percentage of the time is the model right? I'm just looking at that top dog row, and I'm dividing dog by the sum of everything else. And in this case, we always get it right when we see a dog, right? So 4 over 4, 100% dog recall. The precision questions are asking something a little bit different. What we're asking here is, say for dog precision, when the model predicts that it's a dog, what percentage of the time is it right? And so when we're kind of looking at all the predictions now, we're talking about columns, right? Because each prediction is along a column. So in this case, we're dividing dog, top left, by the dog column. We have all the different things we predicted. We're going to get 4 over 6. And then similarly for cat precision, we're dividing cat by that cat column. We see that there's perfect precision here. And hopefully what you can see is that that they're making different kinds of mistakes, right? For the cat, we're great on precision, but we have a recall problem. For the dog, it's the opposite. We have perfect recall, but poor precision. And so these kind of 2 metrics that are kind of showing an error, right? Cat recall and dog precision are 2 ways of looking at that same problem. Sometimes we see a cat and we think it's a dog. The opposite is not true. I'm not going to talk about it more here, but I just want to give you some exposure to it. Often people try to reduce these numbers down to a single score. For example, there's something popular in machine learning called the F1 score. And a lot of these kind of simple scores are just combinations of these other metrics like precision and recall. Right? So these are kind of building blocks for other metrics. So I'm going to head over and write some code for this to Jupyter Notebook. And in this case, I have my confusion matrix converted to a data frame, and I'm showing it down here, like so. Kind of similar to one in the slides, but the numbers are larger now, and I also have a horse. And so the diagonal is good, right? So I can see this is actually not doing too bad, right? I have a lot of large numbers on the diagonal. I see that there's a horse problem. When I see a horse, it actually 90% of the time thinks that's a dog. The other problem I have, right, the other big number that's not on the diagonal is right here. About half of the cats it sees get misclassified as dogs. Okay, that's a problem. So what I'm going to do is I'm going to look at, I've already produced this confusion matrix. I want to look at things like accuracy score, recall score, precision score, then finally this new metric balanced score that I'll introduce. So first, let's take a look at the accuracy score. So I'm going to run accuracy score, and I need to feed it in the actual values and then the predicted values. So I'll do that. Actual and predicted. These are the two lists that I used to construct my confusion matrix. And I see that, oh, let me just run this again. And I see that the accuracy is 78, well, it's about 80%, right? So that seems pretty good. And the key thing to note here, right, is that when we have all these different classes, right, it might seem like we're doing good overall, but there might be cases where we are making a lot of mistakes, right? So for example, when we see a cat, we end up being wrong half of the time. Worse, when we see a horse, we're wrong 90% of the time. And so these other metrics are going to help us dig in and actually identify that. Okay, so let's say I wanted to look at recall for the horse, which I'm expecting to be 10%, right? When I see a horse, we only know it 10% of the time. So one way I could do that is I could, in my confusion matrix, I could get the horse value, right, from that bottom right, and I could divide it by the sum of all the values in the horse row, right? So I could do that, and I get 10% just as I expected, right? The shorter way to do that would be to use this precision score function that's actually built in to sklearn, right? So I'm going to call this thing, and so I have the true values and the predicted values. So I'll say actual, predicted, and I actually get an error here. And it's complaining about something called multi-class versus binary. These metrics are kind of set up for the simple cases where our two classes are just false and true, as opposed to 4 cases like dog, cat, mouse, horse. And so I have to clean that up a little bit. And the way I'm going to do that is, well, first off, let me expand this a little bit. I have to change this average value, right? So there's different ways to kind of summarize information. And I'm just going to set average to none. And actually, no, it's none like that. And then what it's doing is it's actually giving me 4 recalls, 1 for each of these classifications. Now, the order might not be the same as up here. And so I'm actually going to pass in these labels as well to make sure that, that I can kind of actually compare these numbers to the different values, right? So what I see here is that in terms of, actually I want to do recall first, I'm sorry. I'm going to do recall first. And so for this recall, right, I'm going row by row. And what I see is that recall for the dog is perfect. If I see a dog, the model is going to recognize it as a dog. It's also perfect for mice, right? If it sees a mouse, it's trying to recognize it as a mouse. For cats, right, if it sees a cat, 50-50 on whether it will correctly identify it. And then for horse, only a 10% chance that it correctly identifies it. Okay, those are my 4 recall numbers. Sometimes what I'll want to do is I'll want to kind of see how I'm doing overall by taking an average of those, and I get 65% in that case. And it turns out there's a special name for this average of recall scores, and that special name is the balanced accuracy score, right? So before, this accuracy score was saying, hey, we're doing 80%, but now if I actually do this balanced accuracy score, it's only 65%, much worse. And in some ways this is more meaningful. The only reason we were very accurate before is we were seeing very few horses, right? Even though our model is terrible with horses, we could just a good score because there are not many horses in the model, right? So when we're using these balanced metrics, it's trying to take into account for that. It's trying to say, even though we have more dogs than anything else, really, we're going to consider these 4 classes equally important in terms of coming up with our score. This will be a great one to use if you have a lot of imbalance in your data set, right? And accuracy can be a little bit misleading in that case. Okay, so that was the recall score. Let me similarly, instead of this, I'm going to actually do the precision, which I guess I was already doing earlier inadvertently. What happened there? There we go. So I'm going to paste that. And instead of that, I'm going to get this precision score. And now I see something different, right? I see that actually we do perfect on everything except the dog. And why is that? So when I'm talking about precision, I'm really going column by column. And what I actually see here is great, right? Except on the diagonal, I only have zeros in each of these columns. And so that means if this model is predicting a cat, a mouse, or a horse, it's probably right. Only when it's predicting a dog is there a good chance that it's making a mistake, right? In that case, only 2/3 chance that it's actually a dog, right? So this model likes to predict dogs a lot. If it predicts something else, it's sure. If it predicts a dog, it's only kind of 2/3 sure. All right, so that's we talked about accuracy, recall, balanced accuracy, which is an average of the recalls, and then precision. One last thing I want to talk about is binary classification. And so for binary classifications, instead of cat, dog, mouse, we have just false and true. And so I'm computing the confusion matrix here for that. And if I want to, I can compute these same metrics like I did before. So for example, if I do a recall score down here, I can pass in false and true for my labels. And why is that unhappy? Maybe because I didn't run this yet. There we go. I can run that, and it's telling me, okay, row by row. In that first row, 1/3 is correct, right? So, and in the second one, 70% is correct, right? Those are my 2 recall scores. So I can do that just like before. But it turns out when we're dealing with binary classification metrics, people will often just talk about they'll just talk about recall and precision without specifying what class they mean. And when they're doing that, what they're talking about is the positive class, right? So if I just talk about recall in general, I don't want that. I'm just trying to talk about recall in general. Look, I'm talking about that positive class. And the same thing for precision. And actually, this is probably the majority of the cases you'll see precision and recall used as kind of in this special case where I'm having a binary classifier. So just know that when we're doing that, we're talking about the positive class. Hello, in this video I'm going to be talking about 2 topics. One is regularization and the other is standardization. Standardization is something that we're going to have to use a lot in this course and understand. And it's relatively simple. Regularization is a very complicated topic and might require a lot of time in a more advanced machine learning course. I'm not trying to get into any math regarding regularization. I'm just going to try to give the kind of simplest intuition, and we aren't going to get deep into it. But I just want you to know that that's an important and deeper topic. So in terms of things that we've already done, we've been using logistic regression a lot. And a problem that it has that I haven't talked about is that it's very sensitive to scaling. And so, for example, you might have a data set and there might be some numbers in it with specific units. And you might get one result if you do the classification. If you change those units, so for example, maybe you change miles to feet, you might get a different result, which is of course not what we want. We just care about the actual kind of information, not what units somebody arbitrarily chose to use. Why is that? Well, it's because logistic regression is applying this technique called regularization, which tries to use smaller coefficients and in general not have a very large coefficient on just one of our features. You can imagine that if I have lots and lots of feature columns, that just by chance, maybe one of them does better on the training data than others, even if the other feature columns are kind of still somewhat useful. And so what I wouldn't want to do is just by chance choose that best one, because then it won't work well later on a test data set. Regularization basically is providing a motivation to use multiple features and not consider one too heavily, even if that would do better in the short term. So logistic regression does this. Linear regression, which was the first model we learned in this course, does not. But there are also things very similar to linear regression that do, such as ridge regression and lasso regression. We're not going to talk about those at 320, but they're important and used all the time. And so know that this regularization thing is a big deal. So what would we really like? We don't want our model to be sensitive to units. We would like to standardize it in some way so that we have the same numbers going in regardless of what the original units were. So for this example, I just made up kind of a fake scenario. We're measuring some sort of quantity in the real world 3 times. And based on it, we're trying to predict what sort of category it's in. And the category will either be true or false. The underlying rule is that when the true length, which we don't know, is bigger than 5, then the category is true. If it's less than 5, the category is false. And so these 3 kind of noisy measurements, even though they don't tell us exactly what the true length is, they give us some information about that can help us guess whether it's true or false. So here I have that data, that fake data I'm talking about. The Y column here is the category, and then I have my 3 measurements, x1, x2, and x3. Let me just talk a little bit about how I'm generating this. So under numpy.random, there are a bunch of functions that will generate random data. I'm doing a normal distribution here. You can sample from different distributions. If you don't know what that means, that's fine for this course. But basically, I'm generating 1,000 random numbers with an average of 4 and putting them in here. And so this will be an array of numbers. And then I'm saying, well, whenever that's 5, greater than 5, I want to have a true, otherwise I'll have a false. When I'm looking at this data frame down here, true feet does not directly go into any of these into any of these columns. It's unknown. But category does, and category is what we're trying to predict. So how are we going to try to predict if we don't know true feet? Well, I have these 3 other columns, which are basically just true feet plus some random noise. So if I look at it down here, let me look at this first one. All 3 measurements were less than 5. So it makes a lot of sense that I'll predict that the Y is less than 5. Maybe I can even look at some more cases here. I wonder if I can see where it's true. Let me do that. So I can see some other cases here where it's true, right? In this case, all the measurements were greater than 5. So I say it's true. This is kind of a more interesting example. This number is very large, right? One measurement was like almost 7. And even though the other 2 measurements were less than 5, this was enough of a signal that the model decided it's true. Well, it's true overall. And so hopefully the model will decide the same. Okay, so that's the data we're working with. And let's see if we can train a model to try to predict this. So I'm going to create a model, and I'm going to use a linear or logistic regression model. And I'm going to fit it to my data. And so I'm going to have some X and some Y's. For my Y's, I'm just going to pull that Y column from my training data. And for my X, I want to pass in a list of all my columns that contain features. So X1, X2, and X3. And I'm going to be using these again, so I'm actually just going to put this in a variable called X columns. And then I don't have to keep typing that whole long thing every time. And so I fit it, and that's great. And so pretty soon I'm going to look at the coefficients for this model, but before that I just want to, as an aside, see what accuracy it has. If I want to see the accuracy of a model, I can just say, instead of fit, I want to score. And then to be realistic, I should score it on data that I haven't seen before instead of the thing I trained it on. Right, so this is kind of a better test. And I see that it has 89% accuracy. Is that good? 89% seems high, that we would be right that often. But let me show you why it's not necessarily. If I look at this Y column, I see it's almost always false. And indeed, if I say value counts, I can see it's only true less than 20% of the time. And I can actually just divide this by the length of test to see that. And so what this means is that even if I had a very naive model that just always says false, I would be getting 81% accuracy. 89% is better, but in that context, it's not so amazing, just given that there's so much skew in that column. Okay, so after I look at the accuracy of a model, the next thing I'll often want to look at are my coefficients, and I like to plot those in some way. Oh, my model coefficients. And I see those are right here, and I'd like to have some sort of bar plot. So I know that these things are paired up with these x columns, right? So this is the coefficient for x1, so on and so forth. And so the way I'll often make such a bar plot is I'll say pd.series, and then I will have my y values, and then I'll have index equals x values dot plot dot bar. So on the x values, I'm going to use those column names, and then I'm going to put the coefficients to basically have the quantities that are going to go to the y-axis. And it's complaining that the length of one of these things is 1 when it was supposed to be 3. And so x columns, that's pretty simple there. But if I look at this array right here, what do I see? I see there's, it's really a two-dimensional thing. I can flatten it into a one-dimensional array with 3 numbers. Or if I say -1, it'll make it one-dimensional, but it'll make it, you know, it doesn't matter how many numbers I have, it'll figure it out. So I'm going to put that here now. And now I get this plot. And this is interesting, right? I was talking about how maybe sometimes just by chance we focus more on one column than another. And that happened here, right? x1, x2, and x3 were all equally noisy, but it just so happens that based on the training data, the model thinks that x1 is more kind of more useful, right? That was just by chance, right? And so you could imagine a worse scenario where it picks one column that it really likes and ignores all these other ones that have good information in it. And so the model will try to avoid doing that. Regularization means that we'll try not to put too much weight on just one factor. We'll try to spread it out a little bit. And then if you took it to an extreme, you might imagine that I could have a model where I just look at my intercept, right? My intercept is, you can imagine that being like the average, and the model could just predict that, and all my coefficients could be 0. In that case, well, we always just predict the same thing. And we want to have this, this problem. I guess we'd have another problem that just want to be very accurate. Okay, so I have that. And so let me head back here, and I'm going to randomly generate this data. But this time I'm just going to change the units on this column. And I'm going to change the units to be miles. And so there's 5,280 feet in a mile. So I'm just going to make a comment here. This is feet to miles, like that. And so I have the same kind of data, just different units. So I might hope that my model won't do anything that differently. And so I'm going to run this again. And I see that not too much has changed here. And then I want to think about what's going to happen when I rerun this. So in this x2 column, the numbers are all much smaller now because it's in miles. And so I might expect that to use this, I might have a bigger coefficient on x2 if I wanted it to be just like before. It turns out when I run it, I actually see the opposite. It's adverse to having such large coefficients on one column because of that regularization thing I talked about. So it actually decides, hey, I'm just going to ignore x2 entirely. I have to put a bigger weight on that than I'm comfortable doing to have it be a factor. So I just lost some information there. So I'm using these 2 columns anymore. Now, of course, that's silly, right? Putting a bigger coefficient on it isn't really weighting it more. It's just canceling out the fact that I have different units on it. And so there's different ways to solve this. One is that I could just insist that I have the same units for everything. Other way I could do it is I could try to kind of make this a little more uniform in some way. And so that's what I'm going to do here. I'm going to head back here, and let me take my training data and my actually, where do I want to do this? I'm going to take these x columns even sooner. Actually, no, that's fine. I'm going to leave that there. So I'm going to take my training data, and I want to take a slice of it, and I want to get all the rows, and I want to get columns x1 through x2. And so this is just my features now. Oh, through x3, sorry. These are just my features. And I want to somehow standardize it so that they all have roughly the same scale. And so what I'm going to do is I'm just going to pull this out into this x variable right here. And there's maybe 2 things I'm going to do. One is that I'm going to take the mean of each column, just like that. And I'm going to subtract these numbers off of each column. So I'm going to say that. And so now all of these columns are centered at 0, right? After I subtract away the mean, the average of every column is 0. It turns out that that is also helpful for logistic regression to run faster. I'm not going to get into details about why. That's useful. And then more importantly, I want them to be on the same scale. And so, oops, what happened there? I jumped onto a new column, or to a new cell. And so if I look at this, that's a standard deviation of each column. And if I have larger numbers, well, the standard deviation will be higher. And so standardization, the real key part is that I'm dividing all of this by that standard deviation. And if I do that, I'm going to get a bunch of small numbers that have roughly the same scale. So after I've done this, all of them will have the same average, 0, and then the same standard deviation of 1. And so this would be a better X data. And I can actually put this back in to my training data like this. So I'm going to say this equals my new X data. So I make a note here, I'm going to say manually standardize the data. And so after I do that, I run all of this stuff again. And now I see that, great, X2 is back in play, even though I have different units. It's not getting obsessed with these other columns just based on the units. So this was a good thing to do. Okay, that's what standardization is. Now it turns out that, that to do this right, I have to calculate this mean and standard deviation on the training data, but then I have to use that same mean and standard deviation on the test data. I can't retake the mean on the test data. And so the methodology of this gets a little bit complicated. And so generally we won't do this. Generally we'll have sklearn do that for us. And so it turns out that there's a pre-processing step called standardization, and we're going to use that instead of manually doing this. So I'm going to head back here, and you can see I've already imported my standard scalar. And so I'm going to run this here, and this is skipping now. For my model, right, I'll just actually leave this for now, and that'll be my bad model. What I'll do is I'll create a new model, which will be a pipeline model. And in that pipeline model, I want to have a standard scalar followed by a logistic regression. Just like that. And this one, so I'm going to have to actually create them like that. I have to give them names, right? So I'm going to pass tuples here, so I'm going to call that standard scalar. Okay, I have to put commas to separate these things. And then maybe I'll call this logistic regression, like that. And so this is my new model. And then it turns out all this stuff I was doing before, of like fitting, for example, it can work the same way, right? I can fit just like I did before because I called this new one also fit. And so I can do that. I could also score it like I did before. Let me score it now. And I get something very similar. And then what's going to be interesting is that when I actually do this, when I actually try to get this bar plot, it should show that it's back in play, right? Even though the non-standardized version is ignoring X2 now, this version should show it. So I'm going to run this, and there's going to be a small error here. And the problem is that pipeline doesn't have coefficients, right? This pipeline as a whole doesn't have coefficients, but the logistic regression inside of it does have coefficients. And so how can I get to that? It turns out that any pipeline works like a dictionary, and I can, for example, I can copy these names and use that like a key. And so that would get me my standard scalar from the beginning. Or I could pass in this key, and that would give me a logistic, my logistic regression stage of it. And so from that, then I could actually see, well, what are the coefficients involved there? And I would paste this here instead of what I originally had. And so now I can see that when I have this standardization in play as a transformer before my estimator, it'll automatically do that, and then it'll do the right things as well. If I do my fitting here, it'll calculate that mean and the standard deviation. When I do scoring, it's just going to use the same mean and standard deviation from before. It would not look at that for the test because that would be kind of a methodological mistake. So we're going to be generally doing this whenever we have a logistic regression, unless we have some very special scenario. For example, that the data has already been standardized. So we've been doing a lot of supervised learning lately. In particular, we've been doing regression and classification. Now I'm going to give an example of an unsupervised learning problem, which is clustering. And clustering might feel like it has some similarities to classification, In classification, sometimes I would show these scatter plots where there's different kinds of points. And we were, those points were labeled, right? Maybe there's some red points and some blue points, whatever. And we were trying to find boundaries or rules to separate the different kinds of data points that we had. And we did that based on some predetermined labels that came with the data. We know which kind of point is which. In clustering, we might similarly have some sort of scatter of data or the multidimensional equivalent of that. But the difference is that there's no pre-existing labels on the data. That's what makes this an unsupervised learning problem. The algorithm itself gets to choose the labels. And so there's a million different ways you can choose to apply labels to an existing data set. But we still have some constraints, or maybe I should say like a goal. Our goal is to choose those labels so that we're kind of grouping similar data together, and there's ways to measure that. So clustering is this general problem. There's lots of different clustering algorithms. By far the most famous is k-means, so that's where I'm going to start. And so I'm doing some imports here. Eventually I'm going to be using the k-means that comes with sklearn. But to help you understand how the algorithm works, I'm actually just going to write the code from scratch in this video before we actually start using this one. So in sklearn, there's this dataset submodule that can make blobs, or these blobs are basically clusters. You tell them how many points you want, how many kind of different centers they cluster around, and then something about standard deviation. And that returns two things. It returns x, which is actually two columns, an x0 and an x1, and then a y, which is indicating what cluster or blob each of these points was part of, right? And so I don't really care about y, I'm just going to throw that away. But I'm going to throw those two x values in here, and then I have this data frame just like here. And so what we're going to be working towards is trying to find, are there clusters of different points in here where it's kind of centered around something. And so let me scroll down a little bit before I look at this code. And so here's a picture of those points that got generated. You can see it's pretty random, although they kind of center around three different points. I'm just putting a question mark here for now, because these are unlabeled, right? There's no real category. I just have these two, x0 along the x-axis and x1 along the y-axis for my coordinates. And so ultimately to do this, I have, I'm doing a data frame .plot.scatter like we've done lots of times before. The reason why I'm writing this special function here, km scatter, kn stands for k-means. I'll talk a little bit more about why we have that name, is that I'm going to be wanting to show different symbols for different points. And there's not an easy way to specify a column that gives the type of symbol, right? So we have to loop over that. And that's going to be determined by this column called label, if there is one, right? Not necessarily, right? And so this is automatically going to be plotting, well, I just have the comment here, right? It's going to be plotting x0 along the x-axis, and so on and so forth, right? So I'm going to be using this as I go forward. All right, so you can probably already see there's three clusters here, and well, we actually know that because we randomly generated the data. But how can we find kind of good indicators for where those are? And those indications are going to be called centroids. We're going to ultimately try to say, well, here's the center of these three clusters that we discovered, right? How can we do that automatically? And so that's a hard problem, trying to find the three best points. An easier problem in general, right, than finding the best answer is to just take a bad answer and make it slightly better. If you know how to do that and you can repeat it, well, that often ends up giving us a pretty good answer in the end. And this was a strategy that we used for gradient descent. It's very pervasive in learning, and it's the strategy we're going to use now for the k-means, right? So we're going to take a bad answer, and the bad answer looks like this. I'm just going to randomly choose some starting points and assign them each a different symbol. And for now, I'm just going to assume that I'm going to have 3 points, 3 clusters here. We'll eventually revisit that assumption. And I'm going to scatter it down here. And so you can see that this is where it thinks those 3 clusters are. And of course, that's horrible, right? That's not where the 3 clusters are. So how can we automatically identify the centers of those 3 clusters? And so the strategy that we're going to use is we're going to alternate between doing 2 things. First, we're going to do something called assignment, which is taking each of these points and putting it in the cluster, just saying it's going to be in the cluster with the centroid that's nearest to it, right? So these three things are centroids. Centroid is kind of a two-dimensional mean, right? So that's the average x0 and the average x1, right? So those are the centroids. And so the k-means, that's the name of this algorithm, right? So in this case, k is just a variable. And so really we have three means or three centroids, right? We want to find the best location of those. So like I was saying, we're going to assign each of these points to the centroid that's closest to it. And that's point assignment. And then the other step we're going to do is we're going to update where these centroids are so that they get closer to the values that are assigned to them. And we keep alternating back and forth between deciding which points go with which centroid, and then where the centroids are. And eventually it should hopefully converge and try to discover these 3 points. And so to do this, I'm going to be building a new class, right? And I'm just going to call my class KM. And I'm going to have an init method. And maybe what I'm going to do is pass in the data frame with all my data. And then people in a lot of these implementations, they would specify something like, well, how many clusters are there? For simplicity, I've already created this data frame of clusters right here, which if I look at that, what do I have for my clusters? I already have the data for these 3 points, right? I kind of did that. And so I'm just going to keep that outside of my class for now, just to keep the code a little bit cleaner. And so I'm going to grab these things, right? So I'm going to say that self.clusters equals clusters. And I'm going to be making a lot of changes to these things. And I don't want to change the original data, so I'm going to make copies of these data frames, just like so. And maybe let's just see that we actually have something here. I'm just curious what is in this label, right? So I'm going to say self.labels equals self.clusters, and I want to look at that label column just like that. And maybe I'll just convert that to a list, like so, and then I'm going to print that self.labels. Okay, so I want to create one of these things, .km, and I need to pass in my data frame with all my points, and then my clusters. Right, and I do that, and what was I doing there? That was a little silly of me. I want to save that in that variable, and cool. Those are my 3 clusters. I'm just choosing cluster names that happen to be symbols, right? So I can easily plot these. Typically, people would just kind of arbitrarily call these clusters 1, 2, and 3. Remember, there's not any label in the original data. The original data looks like this thing, right? Where I have 100 rows, and then my clusters actually kind of look similar, right? I have the two x values specifying the center, and then also the label. Okay, so one of the first things I'm going to want to do is I'm going to want to be able to plot this as we go, because we're going to be making changes, right? So I want to grab this code that I had before to just see what's going on, just like so. And I'm going to plot that. And let me see here. I guess I can't just use data frame and clusters because these are attributes now, and I don't want those versions. So I'm going to say self.df and self.clusters. And there we go, right? Our kind of initial state of the system that we want to make better. And so remember, there's these 2 phases that I talked about. We're going to have something where we assign the points, right? So that's going to be one step we're going to do. And what we're doing here is we're really kind of going from clusters to points, right? Based on where our cluster, maybe I should tell them centroids are, where our centroids are, that's going to affect, well, what happens in our points. We're going to assign each point to a centroid. I'm going to have that. And the other thing I'm going to have is update the centers, right? And I'm just going to, by alternating calling this and this and this and then this, we're ultimately going to end up with a good solution to this problem. Okay, so first off, how do I do the centroid assignment? That's going to be the harder one. This function here is going to be a little bit easier. And so, well, what I want to do here, right, is I want, for each of these points, I want to assign it to one of the clusters, okay? And it needs to be the closest one. So maybe the first thing I'm going to do is, here, let me just do this, km.dataframe. I'm going to add some columns here, right? And this is one of the reasons why I copied that data frame when I started. I'm going to add a column for each cluster that specifies how close this point is to that cluster. And then once I've added those 3 columns, then I'll add yet another column that says, well, which one is closest? Which one do I actually want to be in? Okay, so I'm going to do something like this. I'm going to say, I'm going to loop over all the clusters, right? So, or I guess the labels, and so I'm going to say for cluster, and well, I'm going to loop over this thing, like so. Maybe let me just print this, and the way I want to loop over it is I'm going to do iter tuples. Excuse me. And this is going to give me named tuples, right? So let me do this. km.assign points. Okay, I'm maybe looping over these named tuples, and so I know where the center of each of these things are. Okay, and so now I want to update, right? I'm updating my points in my data frame. And so what I'm going to do is I'm going to look at these columns, right? I'm going to say x0, and I want to compute for each row here the distance between that along the x0 axis and that center, right? So I'm going to take that minus x0, and I'm going to save that as x0 diff, and then I'm going to do the same thing along the other dimension, and then what I ultimately want to do, apologies. What I ultimately want to do is I want to compute the distance between these points and the center of the cluster, right? So I have the differences along these 2 dimensions. So the distance is going to be like this. It's going to be x0 diff squared plus x1 diff squared, and then I'm taking the square root of all that. That's just the Euclidean distance. 0.5 to take the square root, and let me think here. So this is an individual number, right? I'm looping, so but for each pass through loop, it's an individual number. This is a whole column, so this is a column, this is a column. Really, I'm computing all the distances at once. Okay, and so I'm going to say self.df, and let me come back to this. This is going to be those distances. I'm adding that new column. And what I'm going to use for this column name is the cluster that I'm currently in. So I'm just going to put cluster here. And so now if I run this, I'm not printing anything right now. You know what, let me just clean up this too. I don't need that anymore. Or better yet, just delete it, right? And let me look at what happens to the data frame after I run that. Something horrible, which is, well, it's adding these weird things, which what I really wanted to do was to be the cluster name. Let me do that. And now this is great, right? I can see that, my x0, my x1, and that's a point, right? And I can say, well, how far is that from the O cluster? How far is it from the plus cluster? How far is it from the X cluster? And it's closest to the O cluster, so that's ultimately what I want to want this one to be in, right? So what I'm going to do, right, is after I've looped and I computed these 3 columns, is I'm going to say self.data frame and label. I want it to be one of these 3. You know what? Let me just try to poke around down here first to see how I can get to that. What I really want to look at is I want to look at those 3 columns there and figure out, well, which of these columns has the smallest value in each case. And it turns out that there is a pandas function that does that very easily, and it's called index n, right? And normally what that's doing, right, is it's going column by column and telling me, oh, the smallest value in the O column is at position 11, smallest value in the plus column is at position 78. Not quite what I want, right? I wanted to go horizontally, right? So I want to find out, well, which instead of looking at these index values over here on the right, I really want to look at the column index here instead and say, well, which column gives me the smallest? And so I'm going to paste this back, and instead of saying axis equals 0, I'm going to say axis, that's vertical, I'm going to say axis equal 1, which is horizontal, and then I can get all of these classes, right? So I'm going to put this back up in here, and I'm going to run this again, right? So look at my data frame. I run that, and I can see, okay, great. So I have my original data, which never changes, by the way, right? The data never changes. Then I compute the distance to each of these clusters, and then based on that, I'm like, okay, well, this first one, O is the smallest number, so that's an O cluster. Same thing for the second one. The third one, the smallest value of these three, is under the X column, so that's in the X cluster. So I've been able to assign all of these points, and so let me just show you what's going to happen, right? Let me run this again. So here are the points. If I do the assignment of points, you're going to see that instead of question marks, it's saying what each of these are, right? So you see that this circular cluster is really big. It's actually kind of capturing most of these. And then this one has the opposite problem. We have one actual cluster, and it's being shared between the plus points and the X points over here, right? But it is some clustering, and now that we've actually kind of started with a bad answer, we can make it better. And the way I'd like to make it better is that now that I've kind of decided, well, which points are in the circle cluster, I can kind of decide where that circle cluster is, right? I can see that at this red circle here, that's not a very good real center because that's way to the right of all of the points that it's representing, right? And so that one's going to be a little bit easier now. We're actually going to update these center points. Okay, before I do that though, let me do one other thing. Sometimes, notice how I'm kind of calling this one and I'm calling this one, and each time I say km, km, km. When people don't have to return anything from their functions, right? I don't return anything here. What people will often do, right? Sometimes you'll see this, is they'll just return self, right? And the advantage of that is when I call this, it does some stuff, and then it returns km. And because it's returning km, I can just kind of chain this along like that, right? So that's one reason you often see people just returning self in a method. And so ultimately, we're going to be doing the same thing down here, right? But let's actually update these centers and try to do something. And the easiest way to do this is with a group by, right? I want to, if I go back here, let me do this. I'm going to look at that data frame again. Ultimately, what I want to do is I want to find the new centroids, which are kind of the average of these columns for each label. And so the way I can do that is I can say group by label. That gives me this weird, let me just stop plotting for a moment. That gives me this weird data group by object. And but then what I can do is I can compute the means on it, just like so. So this, when I do a group by, right, that's when I go to the index, right, over here on the left. Then I'm kind of getting the mean over all these other columns. And you know what, there's too much stuff there, right, because when I'm computing centroids, I don't really care about the averages of these anymore. So I'm just going to do this. I say I just want my my X columns, right? And then the last thing that's a little bit weird is you noticed before, like when I started, label was just a regular column. The group by made it not a column; it made it an index. But I didn't really want that, so I'm just going to do a reset index here, right? So this little line here, right, this one line, is a quick way to compute what I'd like the new clusters to be. You see it has all the same data as before, label x0 and x1, right? But now, instead of, my data started off randomly, right, horrible, right now I'm actually having some sort of meaning to it, right? I'm actually saying, well, let's put our clusters at the center, or our centroids at the center of the cluster of data that they're representing, right? So this one's going to be very simple, right? They self.clusters equals that, and maybe let me just I'm going to split this up, right? So I'm just going to say clusters equals that, and self.clusters equals, right? So the first step is I'm just getting the mean, or the centers, right, of each label, and then I'm just pulling out the columns I want and fixing it up so it's in the original shape, right? Okay. Let me do this. I haven't called it yet, right? I just called the one we did before. That's the one we usually start with. But now I can do this, right? After I've assigned those points, now I can run the other function and make it better, right? So maybe, let me actually do this. I'm going to just plot it here. am.plot. But let me just look at the original. So the first off, I don't know anything, right? It's just everything's random. Then I do an assign points. Okay, that's good. And then after assigning the points, then I want to do what? I want to update the centers. And let me just do a quick experiment. I wonder if I can just even put this together in this one. That's trying to make my life a little easier. Great, I can see those two things, right? So, right, so the data started looking like this. I'm going to assign the points to a cluster and then update the cluster centroids, right? So here I update the points, and then you can see. Wait a minute, what happened here? Let me just try to start. I ran it twice. I'm sorry. All right, so you can see the first thing it did, right, is it assigned the points, and then it moved it over. You can kind of see that, this first one's assigning the points, the second one's updating the centroids. You can see that a couple of things happened, right? Like this red circle moved to the left to be closer to where it's supposed to be, and then this plus is kind of encroaching in. There's no reason for it to be hanging so far out. And so if I run these two steps again, like this, it's trying to get even better, right? So I'm going to run that again. And now what you see, right, is not much happened. Not much happened. Well, the red points didn't move originally, right, and not much happened over here on the left. But you see what happened down here, right? This plus sign kind of grabbed some more points after it moved in, and so since it's grabbing those points, X's remaining points are kind of have a center of gravity more to the left, right? So when I update again, I'm kind of bumping that X a little bit more to the left, right? And if I keep running this, right, it should keep bumping it farther and farther over, right? If I keep updating this, it might take a few times. I don't know why it got stuck there. There we go. And so you can kind of actually see I've run into a problem here, and the problem is that I've hit a local minimum, right? I can clearly see that it will be better if this red point, this red circle, bumps up here to the top, and then this X kind of grabs the cluster down here, but it's not doing that because it basically has to get worse before it gets better, right? So it kind of hit what we might call a local minimum. And so, well, how do I solve that? It turns out there's not a bug in my code. I got unlucky, and I wasn't anticipating this will happen, but it's a nice opportunity to talk about it. And I got unlucky because of where these starting clusters were, right? I kind of randomly decided where those starting clusters were, and they happened to be a point where it didn't kind of gravitate towards the three actual clusters. And it turns out that this is a problem in every implementation. If I go to the real one, it will have this thing here, which is the number of times we should try running the algorithm. And each time, right, it kind of starts off with different starting points and then randomly updates it in the hope that it converges, right? And so then it'll take the best of those. And so I wasn't anticipating that happening during this demo, right, because it didn't happen when I practiced before, but I'm going to redo it now. So I'm going to leave my data alone, right, and I'm going to see what happens when I come up, when I kind of randomly generate my starting points. So I'm going to start with these as my 3 starting points now. And remember the default, right, when we're eventually using sklearn, is we're going to start over 10 different times and see what happens each time. Now when I run this, let me, I don't want to have any old plots that are confusing things. I'm going to do this. I'm going to say, that's my starting point. I'm going to say km assign points plot. That was what it was called, right? Assign points, and then update. Second step, update centers, right? So I'm going to do that. And okay, I can see that I've assigned the points and then updated the centers. And now I can see I got luckier this time, and it's not perfect, right? I can see that at this point there's still some weirdness, right? That this one is reassigned over here. But if I keep even just a couple passes, it actually quickly finds out where the three clusters are, right? And usually be somewhere in between there. Maybe it takes a few times to actually converge on the right thing. Okay. In the last video, we built our own k-means class. In this one, we're going to be learning about how the one that comes with sklearn works. And usually you'll want to do that because it works, it kind of gets all these tricky details right. For example, you can easily have it automatically generate varying numbers of starting clusters. It will often have strategies that are smarter than pure randomness for choosing the positions of those before it runs the algorithm. It generally has some logic around when it has been updating the centers enough and it's not going to get any better. And so you can set an upper cap on that, but it's not going to do it more than necessary in general. So overall, you're going to want to use k-means that comes with sklearn rather than rolling your own. So the k-means actually has these three methods with it that we need to know. We have fit, which is not surprising, right? We've seen fit for both transformers and estimators. What's a little bit strange about it is that it has both transform, like you might expect for a transformer, and predict, like you might expect for an estimator. So k-means has some similarities with both transformers and estimators, even though estimators and prediction is a little bit, it's kind of a strange use of it, right? Because we aren't predicting some label that was given to us. We're both coming up with the labels and predicting them at the same time. So it's not really a classic prediction. So I'm going to just show some rough code or kind of data to demonstrate what these three are doing in the context of the code we wrote before we actually dive into using k-means. So before in our class, we saw that we had these assign points and update center, and that was the real core of what we needed to do. And a fit method, what it'll probably be doing is some sort of loop like this for I in range of something. It's just going to be calling both of those. It'll call the assign points, and it will call the update centers, and it'll do that a bunch of times to try to find the right answer. And how many times is that? Well, we're going to call that number of times it does that the number of epochs, right? And so I'm going to say epochs here. And like I was saying, right, in the actual k-means that comes with sklearn, this will be an upper bound, right? If it sees that this is not improving anything further, it might have some break that happens if it's already done. If not getting any better. I'm not trying to do that. I'm just trying to write kind of rough code to give you an idea of what's happening. And so when we do this, right, on our version, I plot this at the end, hopefully it's solving this and kind of updating those points. And indeed it is, right? It's kind of figuring out where each of those centroids should go. So that's the fit method. Now, in the process of doing this, we created a lot of supplemental information for our original data frame, right? So this was our original data frame that just has some points. And in contrast to that, we have this data frame that the k-means class was using with some extra information. First, we have the distance to each of the clusters. And that can be useful information in and of itself. But looking at those three distances, we can figure out which number is smallest. In this case, number in the x column is smallest. So this is going to be, this row is going to be in the x cluster, right? In this next one, the O number is smallest. So we're going to be in the O cluster. And so when we're looking at, let me actually just shorten this up a bit. When we're looking at using k-means for either transformation or prediction, the only difference is whether we're using these distances or the labels. And so let me do the transformation first, to just show you what we'll get there. We'll be effectively getting this data. That's what we'll get out when we do a transformation in k-means, and I'll eventually talk about how that's useful as a pre-processing step before we do something like logistic regression. And then for prediction, all we're really getting is, well, what group does it fit nicely into? And again, right, this is not really like classic prediction because we're both deciding what the labels are and deciding which points go with each label. Okay, I'm going to use k-means on this same data from k-means from sklearn this time instead of our own. And so I'm going to say km equals k-means. And there's a bunch of configuration options here. For example, how many clusters we want to start with. I'm going to say we would like to start with 3 of them. And then what? We can say km dot fit. We always have to do a fit regardless of whether we're going to do a transformation or prediction next. And I want to fit to that data frame. So let me just look at that one more time. Data frame dot head. So I want to fit that data, and we do. And once we do that, then we can do either of those things. We could say transform, and there might be some cases where this is a kind of a training data, and then we're trying to apply our clusters or force our clusters on some second data frame, so maybe some test data. And it'll be very common though that we want to do it to the same original data. And so when I'm doing this transformation here, I saw, well, I have 3 clusters, and that's why I'm getting 3 columns of numbers here, right? The 3 distances for each row in my original data set. And it's very common, right? Rather than doing fit and then transform, why not do both at once, just like so. That would be a fine thing to do. The same way I can also do a fit predict, and then instead of saying, well, which group is it in, it's trying to tell me specifically, oh, you're in group 0, you're in group 2, so on and so forth. And so something we might want to do, right, is that I might want to create a copy of my original data frame and then add this prediction in. And I'm going to say, well, what am I going to say? I'm going to call that cluster, right? I could call it a classification, something like that. And let me actually look at this now. Right, I can see, well, these are the clusters that it's predicted to be in. Maybe I'll look at the tail to see some others, right? And so I could plot it, and I could assign different colors to the different clusters if I wanted to, right? I could say dot scatter x equals x0, y equals x1, right? We're having x along both dimensions. You get those 3 things. But I'd really like to see what color they are, so I'm going to pass in color equals data frame 2 of what cluster you are, and you notice one of these vanishes, so 0 ends up being white. And so what I should do is I should pass in a different color map. And so let me head over here and look at the different color maps in matplotlib. Cluster 0 is not more similar to cluster 1 than it is to cluster 2, right? So I don't really care about getting what is called a sequential color map, something like that, where it's kind of on the spectrum. Really, 0, 1, and 2 are just different categories for me. So I'm going to be looking into the qualitative color maps, and I'm just going to go with this one here because it's a nice set of colors, and I'm not trying to have more than 10 clusters. I'm going to do that. I'm going to say I want the tab 10 color map. And now I can see it's actually giving those different colors, those different groups of points. If I wanted to, I could also look at the centroids and draw that on top of here. And I get the centroids like so. I can say k-means dot cluster centers. And what am I getting here? Well, the coordinates of each centroid are like a row here, and I have 3 centroids, and that's why I have 3 rows. And so I could absolutely wrap that up in a data frame, and I could plot it, right? I could say plot.scatter, and I could say, well, the x is x0, x is 0, y is 1, And I could plot those 3 points, and let me just make them larger and red, right? So I'm going to say color equals red, size equals 100. Actually, use S here, and I should really combine this with what I had before. I can actually see the centroids, and to really make it work, I have to say that it should use the same region, right? So, let me just split this up here, right? It's getting too long. Centroids, dot plot, dot scatter, same AX. And so I can do all that same stuff, just like I did with our own version before. Okay, let me address an issue, which is, how did I know that we should use 3 clusters? And, well, the answer here is that I just kind of eyeballed it. What if there's like 20 clusters, right? That might not be so easy to do. Or what if instead of having nice 2-dimensional data, I have x0, x1, x2, x3, x4, x5? It won't be obvious beforehand how many clusters there are. And so the strategy that you'll do is you'll try a different number of clusters and see how well it does. And this measure of how well it does is called inertia. And so I can look at inertia in our data like this. And well, what is this measuring? It's measuring the average squared distance from points to nearest centroid. That's what that means, right? So for example, this one over here is actually kind of far from that centroid, right? So that'll contribute a lot to this score, whereas this one right here is really close to a centroid, right? So hopefully everything's kind of neatly around a centroid, and of course the more centroids I have, this number will go down. This inertia number will go down, right? Lower is better. Right? It means, well, no, the number means everything's near a centroid. And so what we'll do is we'll actually try different numbers of clusters and see how quickly inertia drops off. So let's do this. So I'm going to go back and kind of grab all of this stuff I had before. And so I'm going to grab this. And actually, let me do this. This is what I really need. I am going to have a little loop like this, and I don't even care about making the predictions anymore. I just want to know that inertia score. I'm going to say inertia. Oh, score. Okay, and so you can see what I'm going to do here, right? I'm going to try different amounts, and of course, as I add more of these things, the inertia goes down until, well, if I have the same number of clusters and points, then luckily each point hits its own cluster. So I'm going to have a loop here. I'm going to say for k in range, and I want to have 1 to 10 clusters, right? So k, that's why it's k-means. K is the number of centroids, and mean refers to the fact that a centroid is kind of the average of the other xy values. I run this thing, and I want to put all of these in a dictionary, or better than a dictionary even, a series, right? So I'm going to say scores equals a series. And so I'm going to do it like this. I'm going to say scores of k equals this thing, this inertia. I'm going to try running this, and when I'm all done, right, I think there's maybe some issues here still. One of the issues that's actually relatively new in Pandas is that they don't like you to leave it ambiguous what the type is going to be. So I'm going to be very explicit up front. This series is going to have floats. And then the other thing it's complaining about is, well, I have a key error of 1. And the reason why I have that is because when I just put brackets after a series, it's guessing whether this is an index or an integer position. And now it's guessing incorrectly that it's an integer position, right? So it's guessing this, which of course doesn't work. If I change it to that, voila, I can get my scores. And once I have my scores, of course, I can plot my scores. Like so, and I should also do this. I should say that put some labels here. The X label is k, which is the number of clusters, and my Y label is what? My y label is the average squared distance to your nearest centroid, right? And so when I'm looking at this here, I see that having 2 centroids is much better than having 1. So there's 2 very clear clusters. Going from 2 to 3, another big improvement. After that, doesn't make sense to have 4 centroids, right? That's not going to give me much improvement. Let's try running this again, right? I'm going to run it from the top, because sometimes these clusters will tend to overlap each other. So just because, way back here, I created 3 clusters, doesn't mean there's going to be 3 clear clusters at the end. So let me just run this again. And here, right, it's not as clear. Is that 2 clusters or 3 clusters? And not surprisingly, well, there's less benefit going from 2 to 3. Let me just try running it a couple more times, get some more intuition here. Okay, so that it's very clear that we want to go to 3. I want to see one where it's really overlapping, but it's kind of a matter of luck here. What about that one? Not so much benefit going from 2 to 3, right? Because these 2 are overlapping each other so much, right? Okay, so that's what you'll often want to do. So one of the use cases for these things is that you will create a plot like this, just so you can say something about your data. You can say how many kind of distinct clusters there are. And that of course is a matter of prediction. Next time I'm going to be talking about how we can do, where was my notes? What are the uses for these transformations? Why might we want to get data about the distance to each of the clusters? In the last couple of videos, we've been looking at how we can use k-means to identify how many clusters there are in the data, and that can be useful in and of itself. Another common strategy is that we'll use k-means as pre-processing for another stage in our pipeline. And more generally, right, you might apply some unsupervised learning technique like k-means or principal component analysis to create better inputs for a supervised technique, for example, logistic regression. Right, so I'm going to do that here, and I've really tried to create data that will really make this work well. And so here you can see on the left both my training data and my test data on the right. And what you can see in the training data is that I've created 5 clusters here, and these clusters are kind of right on top of each other. And out of the 5 clusters, 4 of them have black dots, and 1 of them has gray dots. And other than that, there's just gray dots kind of randomly distributed throughout the space. And then on the right, we want to predict that. And so clearly there are some patterns here. For example, as a human, I might predict that these are in a similar area as this cluster of black dots over here. So I'd probably guess that these are black. And then other dots, right? Like if I'm saying in this space right here, those are probably gray, because in the training data, those were gray. And so certainly it would be hard to draw a single line that separates the black dots from the gray dots for the purposes of a logistic regression. So we're going to have to do some sort of pre-processing. Okay, so I'm going to create my pipeline down here. P is a pipeline, and a pipeline is just a list of steps. And the last step, the most important one, is going to be a logistic regression, like so. And the first one is going to be standard scaling. Standard scaler, like so. And then eventually I'm going to add in k-means as a pre-processing step to help logistic regression work better. And so I'm going to do this. I'm going to fit my model, so p.fit. And what do I want to fit to? Well, I've already taken my data frame up here and split it into training and test data. And I can see that my 2 input columns are x0 and x1. So I'm going to just put those in a variable here. I'm going to say x columns is x0 and x1. Then my y column that I'm trying to predict is just y. And so I'm going to predict on the training data, or fit on the training data, those x columns. And I'm going to compare that to my y column. And then after I do that, I want to score how well does this classifier work. So I'm going to score it on my testing data. And so I run that, and I see it's not doing very well, right? It's only getting about 63% correct because it's hard to separate those black dots from the gray dots. And that's because when I just have a regular logistic regression, it has to only put a straight line there. So if I introduce k-means as a pre-processing step, let's try that. Okay, create k-means here, and let me specify the number of clusters. I'll say n clusters equals, let's say 3 first. Let me try running that, and oh, what happened there? I have an extra parenthesis just kind of randomly. There we go, that's where it's supposed to be. Excuse me. Okay, so still not very good because there's not enough clusters here, right? I guess the original there are 5 clusters. If I try jumping up to 5, you can see that I'm doing significantly better. But if I go up to something like 10, better still, right? I can kind of capture the different areas and realize how close they are. So having more clusters when I'm doing this pre-processing is generally not going to be as problematic as having a few clusters. So what's happening here when I'm taking the input variables to this? Well, I'm using this k-means step on the data, right? So what this is outputting is the distance to each of those 10 clusters that I identified, right? So I might know as one of my variables, well, what is the distance to this cluster here? And of course, if that distance is small, then it's probably a black point. I might also have another column that says, well, what is the distance to this cluster here? If that's small, well, then it's actually probably a gray point. So this is one way to do the pre-processing. An alternative, which probably works just as well, would be polynomial features could also kind of figure out that more complex boundary between the black and the gray.